please fill in the speaker release form and turn it in either to the chairpersons or to Bill or to myself, or give it up at the registration desk. So it's quite important that we have that. And as yesterday, it's planned to have a broadcast of all the presentations. So if you have an objection, just let us know, then we don't do it. I checked, actually it worked yesterday, so you could watch it, and it should still be on. And please, if you have not done so, provide your presentations to be uploaded to the room Didymos, where there is a sign, upload presentation. So if you go outside, it's more or less twice to the right, this small room. For some of the coming sessions this afternoon, there are a lot of presentations still missing. So please provide them, that we have them available here. And I believe that is basically it for now. We got some feedback on the group composition and their purpose. But I think before we start the exercise this afternoon, Bill will provide some update and also give some additional explanation what really the groups are supposed to do. And I believe with these, there are a few announcements by Makoto on the local arrangements. Please.
Okay, good morning. I hope you had a nice sleep last night. Okay, so I have 3 announcements. And one is the poster session today. So today, in the evening, we have a poster session from 6 to 8 o'clock p.m. And we will serve drinks and snacks. So please come. And the second announcement is group photo. So tomorrow, before lunch, we will take group photo in this room. So please do not go away tomorrow noontime. Okay? And finally, I found this cable in the yesterday's welcome reception. So if somebody, please tell me, okay? It's a short cable for USB cable. Okay, that's all.
Thank you, Makoto. So then I think we can start with the program today. And today, this morning, we have session 3, NEO Characterization Results. And the chairperson for this session is Line Drube and Alan Harris from DLR. So please take over.
Thank you very much. Good morning, everybody. So we learned yesterday that asteroids have been discovered, near-Earth objects have been discovered in session 2. And we know that some of them can threaten the Earth. And what we need to do, of course, is find out something about their physical characteristics so that we can work out how to deflect them. That's what we're going to do now in session 3. I'm Alan Harris, my co-chair Line Drube, both from the German Aerospace Center in Berlin. We're starting off with a talk by Simone Ieva of the Osservatorio Astronomico di Roma. And the title of this talk, we need a speaker, don't we? The title of the talk is The Italian Contribution to the NEOShield-2 EU project, Results of the First Year of Activity. Okay, and I'll quickly point out NEOShield-2 is a European Commission-funded project. There are several people here from the project who will be reporting on results during the course of the conference. It's led by Airbus in Germany. We'll hear a lot more about it. The first talk now by Simone Ieva.
Thank you, Alan. So for those of you who do not know me, I'm Simone Ieva from the Observatory of Rome. I will talk a little bit about the NEOShield-2 project and specifically the Italian contribution to the NEOShield project. So, as we all know, there is a great diversity among the NEO population. We have completely different physical characteristics among the NEOs. And one thing that is sure is that whatever is potential impactor. If you want to plan a successful strategic mission, the successful mitigation mission, we want to know the physical characterization of a potential impactor. But right now, we almost know 16,000 NEO discovered nowadays, and the situation gets progressively worse because, as we discovered yesterday, at the moment we are traveling at a discovery pace of almost 2,000 new near-Earth objects each year. And it gets worse because only for 15 of them we have physical characterization. So there are several international agencies and like European Union that are trying to coordinate efforts to try to characterize most of them, basically. So inside this, in the framework of the Horizon 2020 program, the NEOShield-2 project was approved by the European Commission, and one of its main aim was basically to undertake a physical characterization of the small NEO population. Why the small and why this particular range? Because 300 meters, below 300 meters is basically the NEO population with the higher statistically likelihood to impact with our planet. And what basically the NEOShield-2 project want to do is to retrieve all the mitigation relevant quantities important for the proper assessment of the risk. So let's talk about size, albedo, mineralogy, shape, density, and internal structure. Here I show you some of the partners of the NEOShield-2 project. We have, of course, organizations from all Europe. We have Germany, we have Spain, we have UK, we have France. Now hereby represent the National Institute of Astrophysics from Italy, and specifically the Observatory of Rome. Specifically of the Observatory of Rome, our task inside the NEOShield-2 project was to acquire photometric measurements in order to retrieve phase function characterization for near-Earth objects and a preliminary, basically obtain photometric colors, so BVRI filters to assess a preliminary taxonomical classification for our targets. And our targets were chosen basically among the NEO population. They were not characterized all, ever, and basically having an absolute magnitude greater than 20, that roughly translates to something in diameter below 300 meters. So we asked telescope time to several telescopes around the world. We've been awarded with a long-term program at the Telescopic Nazionale Galileo in Canary Islands, where we basically we conduct a monthly program to characterize NEOs in BVRI filters. The program is still ongoing. It's going to terminate in September of this year. And at the moment, we have characterized a good amount of data. Of course, we have some problem with weather conditions. And we also obtain some telescope time at LBT to try to characterize fainter NEOs in BVRI GRZ filters. Then, to complete our other task, the phase function characterization, we established an agreement with a telescope in Brazil, the Observatório Astronômico do Sertão de Itaparica, and with the PI Daniela Lazzaro to perform phase curve characterization. And we also have rapid access to the Italian telescope in Campo Imperatore, the 1 meter telescope in Campo Imperatore. So, some results. Why it's important to have an estimation of the photometric phase curve, the phase function, because basically from photometric observation of the same object taking a different phase angle, is it possible to have some constraint on the NEO? So we have some constraints on the of the absolute magnitude, and at the end we also can have some constraint about the taxonomic type, because basically try to modeling the phase curve function, it has some different effect of the opposition. We have some different opposition effects for different taxonomic types. So by modeling properly this curve, we can have some independent constraint about the taxonomic classification. We modeled several NEOs right now. Here I show you some results of the September 2015 run. And through our phase curve analysis, we ran it through an online tool from the University of Helsinki. and we retrieve the absolute magnitude and the two parameters that basically try to, the G1 and the G2 parameters. So here I'll show some results, for example, for these two guys. And from the different parameterization, you can have, of course, constraint about the absolute magnitude. So let's say in some way we have a constraint about the size of the object, and also by modeling the curve, we also can have some constraint about taxonomical types, so the composition. From our long-term program at TNG, at Telescope Internazionale Galileo, at the moment we observe, so far so good, we observe 151 new NEOs, uncharacterized NEO that have no physical characterization whatsoever. And at the moment, we've been able to derive a taxonomic classification for 105. And of course, we use the NEO taxonomy to try to derive the physical nature of our objects. And we basically use three groupings, so the C complex, the X complex, and the silicate complex, the S complex, and several other classes. And I show you here, as example, the two different colors, the V-I and B-R, together with the same parameters obtained from the sample spectra from the NEO taxonomy. And as you can show, the goodness of our taxonomy is confirmed is very good at the end. We had some problem with the basaltic objects. There are only 4 of them at the moment. But we also know from literature and from article before that basically what we are measured here with the B-R is the visible slope of basaltic objects. So we also know from literature that basaltic asteroids have a very different kind of behavior in the visible slope. So again, it's not completely unexpected. We also try to perform some orbital analysis, so to have, so let's say if it is something from the taxonomical type, again, the orbital parameters, and I show here the two most populated macroclass, the carbonaceous and the siliceous class, and we show you here as example that the carbonaceous have a same major axis and aphelion parameter, aphelion values that are compatible with something originated from the middle and the outer main belt, while the siliceous group has basically a same major axis and a perihelion value from something expected from the inner main belt. And here I show you some very nice plot about the inclination of our orbits and versus the MOID, the minimum orbital intersection distance with our planet. And I also show here a zoom of 0.05, that the MOID that defines the potential hazardous asteroids. What I wanna give your attention in this, with this slide is basically that we are looking for something with low MOID and with high inclination requires special attention, because of course low MOID is something that comes closer to our planet. And from a very high inclination, it's very complicated to project and to assess a spacecraft mission toward that kind of objects. But also, what I want to show you here is that at the moment, the most efficient mitigation mission is the kinetic impactor, which is proved to be less efficient for, let's say, more porous carbonaceous and D-types. And so for these reasons, basically, these guys I circled here represent a special attention, because they also in low MOID orbits, high inclination orbits, and from their composition, they seem to be very porous, so they're going to be a careful detailed analysis. So in the framework of our task inside the NEOShield-2 project, we obtained colors for 150 objects, and within phase curve for 14 objects. But most of them basically are still undergoing, because we have a whole new semester at TNG. The project is gonna end in September, and we also have new phase curve characterization from our telescopes in Brazil and Campo Imperatore. So by the end of the project, we expected to have characterization for almost 2,000 new uncharacterized NEO, and this huge amount of data analyzed by the same team will minimize some bias effects that are expected to be inside the study of the new population, and particularly of the small new population that we have very few of little amount of data. And moreover, we identified some carbonaceous asteroids that should require, oh, perfect, a detailed investigation in the future. Thank you.
Thank you very much. The talk is open now to questions.
Yes, I have a comment and a question. The comment is that it is agreed that high inclination asteroids, if they are possible impactors, are more difficult to handle. On the other hand, they are less likely to be impactors, because the probability of impact, roughly speaking, scales as 1/sin⁵. So the low inclination object is much more likely to be the next one to get at us. Second question. All this is very interesting, but what is really needed is the capability, when an object is discovered and found to be dangerous, something which happens in a time scale of a few days, before it is lost, to get spectral information, taxonomy, and so on. Is this possible? That is, do you have a capability of quick response?
We don't have this kind of capabilities because we don't have access to a very quick response to characterization, but there are some other telescopes that I think do this very well. But we can coordinate later, it's okay.
Yep. Other question, yep. Oh, sorry.
So Megan Sayao showed in a range of cases that she considered that while beta typically decreases with porosity, that the reduction in the bulk density can more than offset that. And so that the net result for the deflection for porosity can be positive, can be easier to deflect an object as a result.
Okay, thank you. I think we've got time for another question. If there is anybody that would like to ask one. No. Al? No. Yes?
Which is a corollary really with what Andrea Milani mentioned, and that is that as you go to higher inclination, moid, in a scatter diagram, moid is going to be larger. When you get under 0.05 radians of inclination, you can't not be a PHA, for example. It's just the way it works. The moid can't be greater than 0.05. So there is an inclination effect there too, so it's hard to interpret that graph that you put up there because of that correlation between inclination and moid.
Did we have one more? Very quick, very quick. Yep.
Do you get the light curve data? Sorry? Get the light curve data? Light curve.
Light curve, did you say?
No,
yeah.
Sorry, no, there is another task. We're not in charge of the light curve data.
How to calibrate in order to get calibrate the light curve?
How do we calibrate the color indexes?
Yeah.
Because we have basically we observe several standard stars each night. We have
Okay. Okay, I think we'll move on. Let's thank our speaker again.
All right, the next one is Erik Christensen. He's taken over. We moved 2 slots around, so it's not Moon. And he's going to talk about the status of the Catalina sky survey for near-Earth objects.
Oh, any questions? right, let's see if this stays put. Good morning, everybody. My name is Eric Christensen. Thank you to the conference organizers for accommodating the change in schedule. I'm going to take you back to yesterday when we were talking about the problem of NEO discovery. I appreciated Simone's comments about NEO discovery being a problem that's getting worse. We're certainly doing our best to make it as bad as possible. Oh, no. Okay. So just a quick reminder, the Catalina Sky Survey is a NASA-funded NEO survey project. We are 100% dedicated to the NEO survey effort, and we've been operational in one form or another since nearly 20 years now. We're currently using 3 telescopes in southern Arizona, 2 survey telescopes, and 1 follow-up telescope. And we're staffed at a level of about 10 people, and that's half nighttime observers and half engineering and management. One of the features of the Catalina Sky Survey of our operations model is a very sort of agile, flexible night operations model. At the telescope, we have a skilled observer who is not only responsible for operating the telescope, but for making the schedule, doing the QA, the data QA in real time, making sure that the processing is done quickly, and finally visually validating all of the important candidates and reporting them, and even scheduling same-night follow-up. And this real-time operations has allowed us to do things like discover imminent impactors. We are currently discovering NEOs at about a rate of 900 per year or so, and that is hopefully increasing. So far in 2017, the results seem to hold up. And here we go again. Oh, geez. All right. Here's just sort of a visual overview of the facilities that we use. We have sort of a tiered approach with a range of survey capabilities ranging from small aperture, very wide field, to larger aperture, narrow field, with a supplementary follow-up telescope. And this approach has served us well. It allows us to task each telescope, sort of optimize each telescope to fulfill its own niche. And in context, here are 2 other surveys that you heard about yesterday, Pan-STARRS on the left, Atlas on the right. So Catalina is sort of a microcosm of the overall survey landscape that ranges from shallow and broad to deeper and narrower. We have recently completed a few instrumentation upgrades that have been in progress for a few years now. We've replaced our survey cameras with new state-of-the-art 10,000 by 10,000 pixel CCDs. This is an image of the 1.5 meter survey telescope. And the new detector, in combination with some new correcting optics, increased the field of view of this telescope by a factor of 4, so up to 5 square degrees. And doing that has enabled us to sort of step off the ecliptic. Previously, we sort of concentrated our focus on the ecliptic and a bulge around opposition with this telescope. Now we sort of treat this as an all-sky instrument, and so we're going off ecliptic, and that has basically tripled the rate of discovery of not only the small, nearby fast objects, but also the more distant large objects. I think we're almost to the end of this auto forward here. We put an identical camera on the Schmidt telescope. Here's an image of the detector. You can see sort of a selfie of our founder, Steve Larson, in the reflection there. And so this had also had a significant effect on the field of view, going up to nearly 20 square degrees in a single shot. And so this telescope also surveys the entire sky visible from Tucson every 3 to 4 nights now, down to about 19.5 magnitude. So we're prioritizing very frequent, very wide, and relatively shallow coverage with this telescope. Partially driven by these instrumentation upgrades, we've also had some recent software upgrades. There aren't really as pretty pictures to illustrate these, but these are nevertheless sort of fundamental to our operations. at the heart, Catalina is, like many other telescope or survey projects, is really a software project. And so we've sort of continually worked on improving our software at all levels, from the acquisition. The acquisition is now done by a queue manager rather than sort of a script-based system. So this allows the follow-up telescope to flexibly interleave observations of many objects at the same time, all with different exposure times and cadences and telescope tracking rates. The reduction software has been improved. We're doing better astrometry, better centroiding, better plate modeling, better shutter timing, and improving some other auxiliary software tools like the focus models and the user interface tools as well. This is even less sort of interesting, if you will, than the software and instrumentation upgrades, but nevertheless very important to sort of shore up the infrastructure of the survey. That's the timing, that's the network, that's the computing clusters. And so the net effect of this is that we're covering more sky, we are taking more data per night, doing it more efficiently. We are processing the data in a more reliable and robust and precise way, and we're finding more NEOs. I suspect you probably saw a plot like this yesterday. I just wanted to highlight here the improvement from 2015 to 2016. This was the about 6 months of operation of the 1.5 meter camera minus a few months of downtime of the 0.7 meter camera. And so you can see that we've increased our own discovery statistics, but more importantly, the field has increased sort of overall. We're not sort of just playing a zero-sum game where the surveys take discoveries from each other. We're really doing this in a complementary way. So this is the plot that you show if you're pan stars, because it shows more pink than green. But I wanted to highlight this just to show that we are improving the number of large objects, and again, not at a cost to other surveys' discovery, but we're seeing a net gain sort of across the board. Finally, I wanted to take a couple minutes to talk about a project that we're engaged in to reprocess our archival data. The motivation for this is to provide better astrometry and photometry to the people who are doing the orbit calculations. We have over 3 million images taken over from 4 telescopes over about 15 years, and with a variety of reduction pipelines. As you can imagine, in 2003 when we started, our processing was much less sophisticated. There weren't, the processing power wasn't really available, nor were the star catalogs, et cetera. So we've gotten a lot better at what we do. The best time to be concerned about your archive is while you're still taking data, and so we're very consciously working to protect our holdings and also provide the public with access to these. So these images, as they're reprocessed, plus the auxiliary metadata, will all be available to the public through the Planetary data system. This is ongoing. We expect that we will have submissions starting in the fall of this year, perhaps the spring of next year, and we will start with the nightly data first, and then work backwards into the past. All this will be done under the new astrometry standard, the IAU 2015 80s, that will allow us to communicate more precise uncertainty estimates of our astrometry. A little bit of a look ahead. What we plan to do is we plan to continue to operate the survey telescopes and improve their efficiency. We plan to expand our follow-up activities. The current sort of survey to follow-up ratio is starting to fall behind again after sort of some pretty good years in equilibrium. We're seeing more survey output than certainly the talented follow-up resources can handle collectively. So we'd like to scale up the follow-up, scheduling additional nights on I-52 and expanding to other telescopes in Arizona. And finally, we're looking toward developing what we're calling a broker, or rather than a broker, since that sounds like something is broken, a fixer. We're looking for a fixer to solve the problem, or to enable the problem of tasking intelligently different follow-up resources to targets where they're most needed. And this will be not only to schedule our own follow-up efforts, but to engage with the community to hopefully balance the load over the entire follow-up community. So with that, I will take any questions.
So any questions? Oh, yeah.
Yeah, unfortunately you missed my talk yesterday where I went into the detail of the redetection ratio to estimate total population. One of the big bugaboos of that is that if you are detecting objects with intention of follow-up, that kind of screws up the redetection ratio. I've always assumed that G96 is pretty much pure survey and not follow-up. To what degree am I making a good assumption?
It depends. As we've started to use I-52 more frequently, that's lessen the follow-up burden on G96, but we are scheduling.
I don't even use that telescope. I use G96 and 703.
I'm saying they are correlated, though. As we're using the follow-up telescope more, we're using the survey telescope to do follow-up less, but we're only operating the follow-up telescope part-time. So it can actually be a fairly significant effect or a significant use of the survey telescope's time. However, that's mostly focused toward NEOCP follow-up, which really shouldn't factor into redetection.
The most obvious case is Spacewatch, where Spacewatch 1 and 2, one telescope is essentially exclusively follow-up, and that has to be discarded, but the other Spacewatch I can use.
You also have a question?
What would you regard as sort of an ideal ratio of follow-up to discovery statistics? And I'm thinking more in terms of like the second opposition recoveries. That's sort of like seeing the thing at a second apparition, and sort of a quick thought would be 1-to-1 would be ideal if we recover previous discoveries as often as we find new things. That way we'd be keeping up, but we're not anywhere close to that. So do you have different thoughts on that?
Well, we tend to focus sort of on the new discoveries and keeping discoveries that are made. Right now there are hundreds of NEO confirmation page objects that are removed as not confirmed. This is sort of 600 or 700 entries a year of objects that go up on the page and then are removed because they are not confirmed. Now, not all of those are going to be NEOs, not all of those are going to be even real objects, but if even a quarter of those are real objects, then just by deploying follow-up where it needs to be at the discovery apparition, we could improve our survey output by 10% or so.
All right, thanks. I think we'll go to the next talk. Thanks. And
Okay, now we're moving on to radar. We've got 4 talks coming up on radar. And the first of those is a talk led by Patrick Taylor, entitled Ground-Based Radar Observations of Potentially Hazardous Asteroids. And Patrick is from he's from lots of places. I think the main one being the Arecibo Observatory. Is that correct?
That should be it, yes.
Great.
Yeah, so I'm from Arecibo Observatory, but also USRA. So yes, we're going to talk about radar now. If you're not familiar with Arecibo, this is it right here, just for a sense of scale. All of our transmitter and receiver equipment is in this Gregorian dome here. This is essentially a 4-story building, suspended 500 feet in the air on a 900-ton platform. And for a sense of scale, this dot right there is a cable car with people in it. So there are really 2 facilities that are regularly active in doing planetary radar. one being the Arecibo telescope in Puerto Rico, the other being the Goldstone telescope DSS-14, part of the Deep Space Network in California. So Arecibo, where I'm located, is 305-meter diameter dish with a 1 megawatt transmitter. We work at the S-band frequency, 12.6 centimeters or 2.4 megahertz. We have a fixed dish. This dish doesn't move. All of our control of pointing is based on moving the telescope platform up above it. Because of this, we can see about 1/3 of the sky. Goldstone, on the other hand, is smaller than Arecibo at 70 meters in diameter. It has a slightly less powerful transmitter, but it does work at a different frequency at X-band, 3.5 centimeters or 8.6 gigahertz. Its other advantage is it's a fully steerable dish that can see 80% of the sky. So the two telescopes are really complementary. Arecibo is very sensitive but limited in its field of view. Goldstone has higher frequency and actually better range resolution than Arecibo, and can also see much more of the sky. So they're actually very complementary observatories. So the critical capabilities that we care about in terms of planetary defense that come from radar are we're able to control our signal, which means anything that we see in the echo that's returned to us is any changes are due to the properties of the target itself. So we can very accurately measure how long it takes for us to get that echo back and very accurately measure what frequency that echo comes back at. So that's giving us incredibly precise information about the line of sight distance and velocity of the object that we're pinging with the radar. Essentially, we have a fractional precision of 1 part in 10 million. And every time we detect an asteroid, it provides an estimate of the rotation period because we can measure the instantaneous rotation rate of the object based on how much it Doppler broadens the signal that we sent out. And as the signal strength allows, we can get even further information, including size, shape, and surface features, including essentially surface geology. We can see boulders, concavities, possible craters, things like that on the shapes of these asteroids. And we can do that with spatial resolution as fine as 3.75 meters. Beyond that, we can also get scattering properties by measuring the size. We can figure out we can constrain the optical albedo. We can learn about the radar albedo and reflectivity of the surface, the polarization of the surface. And putting these together can give us an idea of near-surface bulk density and also near-surface porosity of the object. Beyond just the near surface, if we happen to detect a satellite, which radar is it's incredibly easy for radar to find a satellite, which I'll show later. And once you find a satellite of an object, you can map out its orbit, which will tell you the mass of the system. With the sizes, you'll get the density of the system. That will tell you something about the internal structure and porosity of the bodies. And also, just by measuring the rotation rates of the bodies, that can give you an idea. Are they near the spin barrier? Do they have to be, can they be cohesionless? Have they broken past the spin barrier? Do they require some kind of cohesion to hold them together? You can get that information from radar as well. And putting all this together, at its highest fidelity, a radar campaign is roughly equivalent to a spacecraft flyby. And we can do this for orders of magnitude more objects at orders of magnitude less cost than doing highly specialized flyby missions. And in terms of helping missions, we also provide navigational support and characterization of spacecraft targets. In the past, this has included the Hayabusa mission to Yoshikawa, supporting that mission, getting astrometry for the Deep Impact Extended Mission Epoxy to Hartley 2. OSIRIS-REx is going to Bennu, partly because of the extensive information we have from radar observations. And we can also help inform the AIDA mission, our mission, the Psyche mission, and so on. And I was supposed to take that one out there. Sorry, Paul. If you've noticed, every time we go to a PDC, somehow the object always comes in from the south, so Arecibo can't see it. It's always too far away for Goldstone. It's because radar is just too good. It really prevents the threat makers from making a good scenario. So when it comes to threats, radar's ability to improve orbits is incredibly valuable. As I said, we get a fractional precision of order 1 part in 10 million in our astrometry. This astrometry is along our line of sight, so that's orthogonal to plane of sky optical observations. So if you can get plane of sky observations plus radar observations, you have the full 6-dimensional position and velocity state of an object. And because of this precision, you can reduce orbit uncertainties by orders of magnitude for newly discovered objects. You can extend the Earth encounter predictability windows by a factor of several, usually by decades or centuries. And you can determine the subtle effect of Yarkovsky drift, which is changing orbits on very small scales, but at scales that we can actually detect with radar. So as I said, this is invaluable for impact hazard assessment. So at the bottom here, I have 2 of my favorite examples of radar data. They are not very pretty, but there's a tremendous amount of information in these two images. On the left is at the time, a newly discovered asteroid called 2013 LB2. It doesn't look like much. It's a single pixel, but we know exactly where in space that single pixel is. The astrometry from this measurement corrected the line of sight distance to this object by almost the diameter of the Earth. If you're worried about something hitting the Earth, you certainly want to be able to correct its position by the order of the size of the Earth. That one little pixel prevented this object from being lost and requiring rediscovery in the future. It extended its predictability by centuries, so we know where it's going to be for several centuries into the future. And this is Bennu, the target of the OSIRIS-REx mission. This little cluster of pixels doesn't tell you much about the physical properties, but it was able to determine the Yarkovsky drift of this object, which in turn gave us a mass and a density before we even send the spacecraft there. So at Arecibo, we have, in the last 5 years or so, really kicked up the number of observations that we've been doing. We've essentially tripled or quadrupled the number. So essentially since 1998, we've made 667 detections of 595 different objects. This is about 4% of the NEA population. And almost half of that are PHAs, which amount to about 15% of the PHA population. We prioritize PHAs. We also prioritize dynamically accessible asteroids like the NHATs. I won't go into this. Please see the poster by Ann Verke this afternoon. We are also prioritizing those objects that are especially of interest to NASA. At Goldstone, in the last 5 years or so, they've also essentially tripled their output on asteroids, and they also do about half of their detections are potentially hazardous. So if you put Arecibo and Goldstone together, we're essentially doing 100 asteroids per year, and we could probably do at least 3 times more. There's no shortage of things to look at with radar, so we could easily be doing more if we had more telescope time and more manpower to handle it. I just went to the impact risk table on the SSA-NEOS website. The top 3 cumulative impact probabilities, Bennu, 1950 DA, and Apophis, have all been subjects of radar campaigns. Marina will talk about Apophis next. And I'll quickly show Bennu and 1950 DA. This is Bennu from Mike Nolan's work. We have radar images from Arecibo here on the left, synthetic radar data, and what the object looks like on the plane of sky. So we were able to derive a shape model from radar and light curve data and get this roughly 500-meter object, circular equator, kind of these sloped sides. This is sort of the canonical spheroidal shape we see for a lot of these near-Earth asteroids. This is 1950 DA from 2001. This was published by Michael Busch. I'll just skip really quickly to the shape model. This is sort of an extreme version of the Bennu shape, where you see this very pronounced equatorial ridge and sort of sloped sides. This object is rotating at 2.1 hours. It likely requires cohesion to keep it together with this sort of shape and rotation rate. This is one of our most recent PHAs that we observed, 2014 JO25. Lindley showed this really quickly yesterday. It really looks like Comet CG from the Rosetta mission, but shrunk down by a factor of several. This is about 1 kilometer or so in diameter, very obvious two-lobed shape. And it might be a little hard to see here, but you can see great detail of flat sections, possible boulders, possible impact craters on the shape. That was the Arecibo data. This is a mosaic of Goldstone data showing essentially the same sort of shape. We can very easily see how big it is, what shape it is, how fast it rotates. It rotates in about 4.5 hours. So here you can see it go through half rotation as you scroll through these different rows. We also see very surprising shapes. This was a Goldstone target from earlier this year, 2017, BQ6. Essentially the most angular looking thing we have ever seen. It was compared to a Dungeons and Dragons dice by Lance Banner. But you can see just these really strong planar features, very sharp angles between the facets. This is a 200-meter asteroid rotating in about 3 hours. I said we were really efficient at finding binaries. This is one from earlier this year, 2003 UX34, a PHA. What you have is the primary here. It's larger and rotating faster, so it appears bigger and wider. This is the satellite here. This is a sum of, I forget, maybe like an hour of data or so. And so you see the secondary is smearing through here. So if you trace that out, that you could actually get the orbit. Turns out it's a pretty normal near-Earth asteroid binary. Density probably around 1 gram per centimeter cubed. And time is up and it's blinking at me. The last one I wanted to show was Didymos, the target of the AIDA mission. This was observed by radar. It's currently being shape modeled by Shantanu Naidu at JPL. So this will give us a great amount of information about the size, shape, and rotation state of that system before the AIDA double mission gets there. In case you're interested, these are the organizational web pages for Arecibo and Goldstone with our target lists, requests for collaboration, past detections, history, and so on. And to summarize, radar is a unique and powerful tool for post-discovery dynamical and physical characterization of near-Earth objects, and it's invaluable for mission planning and validating mitigation techniques. I didn't really talk about that, but if AIDA goes up there and smashes into the satellite of Didymos, and you want to measure how much that orbit has changed, you pretty much need Arecibo and Goldstone to measure that subtle effect. We can detect about 100 asteroids per year and are capable of more, and we prioritize things that are potentially hazardous or dynamically accessible to spacecraft. And just overall, the population is very diverse, so you need every bit of observational information you can get on these objects in order to properly determine what you need to do to mitigate a potential threat. Thank you.
Fascinating talk, Patrick. Thank you very much. Radar never fails to entertain. Do we have any questions?
We have another Patrick waiting with a question.
Andrea.
Right.
Yeah, just a question about the one with the flat surfaces. Do you have the spectral type for this one?
I do not know offhand. Is Marina around somewhere? Marina, do you happen to know anything about BQ6 taxonomy?
Or an albedo, at least?
I'm sorry?
Or an albedo, or because for me it looks like a metallic object, I would say. Such sharp thing when you want to explain it by fragmentation. I would say it's more like a non-porous body, but depends on the spectral type.
Yeah, I'm just not sure offhand.
Okay. Would be good to get it.
We had a question over here.
Oh.
Okay. I agree that you can provide fantastic data. One of the data which is very precious is about mass and density, in particular in the many cases in which there are satellites. For this is essential for mitigation and also as other scientific usages. As an example, to have the density of a V-type asteroid would be very important for solving problems like the age of Rhea Silvia crater, this kind of stuff. And I know there has been a V-type asteroid which has been observed by radar found the satellite. Here comes my question. How do I find this kind of information? That is, could you please provide it, not to me, but to everybody on the website, a table of all the density and mass data you have derived in such a way that one can immediately see if the data are available or not?
That is something that we're working on. We don't have really a public repository of all the radar data at this point, but it's certainly something we need to work on.
The mass is the most important. If you have, because if you have it, you are the only one to have it.
Okay, I think we ought to move on now. A few more.
Okay. Patrick, could you clarify more for me? That's probably I missed something important. You had written that it was detected 100 of NEOs. Detection means that nothing was known about this object and just new observation, this observation after scanning on someone appeared. My question is if it is real detection or just classification, improvement of classification based on the previous optical observation. Oh, it is real from nothing. You just scan some space and then reveal this NEO.
So we are completely reliant on optical
Yes.
observations to tell us what objects are visible. So when we detect something, it's something that's already known optically. Often there's not much else known about it other than its predicted position in the sky. Once we detect it, we can provide further astrometry and an idea of its rotation rate just by detecting the asteroid.
Detection means improvement of the previous observations, which provide you with the possibility to classify as a NEO this object, yes? Do you understand me or not? I see that some...
well, I mean, if we can observe them, they pretty much are already known to be NEOs.
Already known from optical observations, yes?
Yes.
You classify it then, because detection for me, that's just maybe that's the language. The detection is that obtaining this object, that's revealing this object from nothing. It is detection, the real detection. Okay.
I think what he's saying is that radar does not detect in the sense that an optical observatory detects the first ever observation of an object. They rely on optical observations so that that the objects they observe are already known, basically.
Right, we're not discovering, we are observing known objects.
Okay, we have to move on. Let's thank our speaker again.
All right. And the next one is Michael Busch who's going to talk about Arecibo radar characterization of 2001 CB21, a flyby target for the DART spacecraft. He's from SETI.
Okay, so you heard in the last talk radar observations of Didymos, which is the primary target for DART and for AIDA as a whole. However, while DART is en route to Didymos, it's able to fly by the asteroid 2001 CB21, which the radar team happens to have observed in 2006. So I took the opportunity to go back and look at the data and see what we can say about the object. So CB21, you have overview of the orbit, fairly typical near-Earth asteroid. Last close approach was in 2006. So Earth was here, CB21 was there. Now, at the time, we planned a fairly extensive radar observing campaign. We ended up only getting 1 day's worth of Arecibo radar images, which was October 2nd of 2006. Reason for that was, at the time, Arecibo was still using the very old and clunky diesel turbine as the power source for the radar. The turbine was broken that week, so we were running at 1/10 of the transmitter power. which meant that we have somewhat coarser resolution than we otherwise would, having only 1/10 the signal to noise. We can still get some useful information. So we have a total of just over 2 hours worth of data. We can't get more than that because Arecibo is constrained to look within a certain number of degrees of zenith, and you're limited by how long the asteroid takes to fly overhead. We organize everything here into transmit-receive cycles. We transmit for a while, the signal goes out to the asteroid, comes back, then we switch to receive to listen to the echo. We had a bunch of continuous wave CW observations, just transmitting to pure tone, listening to it. This tells us the Doppler shift of the asteroid relative to the prediction, so we can refine the orbit. And it also gives us information on the radar scattering properties, which I'll talk more about later. We spend most of the time on delay Doppler radar imaging, which Patrick described in the last talk. Resolution in this case is half of a microsecond in the round-trip time delay of the radar signal. So that's 75 meters in line of sight distance. That again is a lot coarser than we would like to have done. In this case, the asteroid is 5/100 of an AU away, and we're running on low power rather than having more signal to noise. So that's why the resolution is so coarse. Even with that, things are pretty grainy. So these are sums of 15 runs each, spanning about 22 minutes of observation time. And there is an echo. There's the asteroid, each image, but it's pretty ratty. Now, there is potential some glinting going on here. So these are a few bright pixels. The asteroid's echo is there, but it's gotten a little bit lost in the color stretch. The relevant thing here is that the visible range extent of the echo is 3 to 4 rows in each of these images. And the echo bandwidth is 3.3 hertz, give or take about 20%, and it doesn't vary detectably from one time during the observations to the next. We have optical light curve data from this flyby. The spin period is probably 3.3 hours. There's a possibility of an alias to 1.5 times that. But either way, over these 2 hours, we've covered a pretty large fraction of a rotation. That lack of variation in the echo bandwidth tells us that the asteroid is not very elongated. So elongation no more than perhaps 1.3 in terms of the ratio of the equatorial dimensions. The echo range extent becomes 4 pixels, and that's about equivalent to 300 meters. Given this roughly spheroidal shape, apparently, we can approximate the diameter as being 600 meters, give or take, about 25%. That's in line with thermal radiometry from Spitzer, so we at least are getting a consistent result. Now, the echo bandwidth, this is the Doppler echo spectrum again, so the previous images collapse down into a single line effectively. That echo bandwidth, that 3.3 hertz, combined with the average diameter and the spin period, tells us we were not viewing CB21 from a high subradar latitude. If you're viewing from near the equator, you get near the maximum possible bandwidth. If you were looking down the spin axis, all the asteroid's rotation is on the plane of the sky, and there's no Doppler shift applied to the radar beam, so the echo bandwidth would collapse down. That's not what we're seeing. So the asteroid was being viewed from near the equator, but beyond that, I can't tell you the spin state with only 1 day's worth of observations from the radar. Now, the relevant thing from this plot, we have 2 lines. OC is the opposite sense circular polarization as transmitted. SC is the same sense circular polarization as transmitted. So we transmit one-handedness of circular polarization. It hits the asteroid, gets reflected back. A single bounce will give you the opposite sense as reflected. If you have even order scattering, you get the same sense as reflected. Generally, these two, you'll see a lot less of the circular polarization in the same sense as in the opposite sense. And here the ratio is about 1/5. Occasionally, we'll see asteroids that are extremely rough on the scale of the radar wavelength, and they'll have much higher polarization ratio. We don't see that here. This rules out some potential compositions. This is not going to be an E-class enstatite chondrite. It's not going to be a V-class basaltic object. There is some possibility of getting additional composition information in the future on CB21. I don't think anybody got a spectrum on it, at least until now. If somebody has that data, I would like to know so that we can cross-compare and make sure what I'm telling you here about the composition is actually correct. Now, the radar albedo is based on just taking the total echo power, comparing it to the cross-sectional area of the object. In this case, it's about 6%. Again, pretty large error bars. That rules out a metal-rich composition, something like Psyche, for instance, which has a lot of metal on its surface. That number will be maybe up to a factor of 10 higher than it is here. This number is consistent with a carbonaceous composition, but also with some silicate mixtures. So beyond that, we can't say too much. The optical albedo here is 0.2. That's relatively high, but again, the error bars are pretty big. But there are both C and S-class objects that have albedos in that range. So it may be carbonaceous, it may be silicate. It is interestingly different from other asteroids that have been visited by spacecraft so far. We have 3 S-class objects, Tutatis, Yoshikawa, Eros. They all have higher radar albedos. We have now also Ryugu and Bennu. They have low radar albedos, but also very low optical albedos. So at least in terms of its surface composition, CB21 will be interestingly different from all the other asteroids that have been visited by spacecraft or will be in the near future. So it's good that we have the opportunity for DART to do this flyby. One thing that is particularly relevant for doing a close flyby is if this thing has a satellite or not. So for that, we've stacked up the data complete all 2 hours of radar imaging. So the primary is here, CB21 is here, and it's all completely blurred out by half of a rotation. If this were a primary and it had a satellite around it, you'd see a single bright streak that would correspond to a small satellite. There's nothing in there. I mean, there's no bright pixels off of the echo down to an SNR of about 6. So there's no satellites in here and that we can detect, and that corresponds to a size limit of about 75 meters, given that the satellite spin period is greater than about 2 hours. Now, there is the possibility of a smaller satellite. There are a few that are known that are about 50 meters across, but nothing large is in orbit around CB21. Now, at the moment, the position of the asteroid in 2022 is uncertain by plus or minus 500 kilometers, 3 sigma. That's with the radar data from 06 and all the optical data set. We can improve that before DART gets there, although DART may be able to handle having a 500 kilometer uncertainty. It depends on how good the proximity navigation is. But the AIDA people can answer that one. But we can improve things because we can get radar observations starting in mid-February of 2022. So at that point, the asteroid is here, the Earth is here. We're catching it on the opposite side of its orbit. So given that we still have Arecibo and Goldstone to work with in 2022, this will be a good opportunity because we're getting the asteroid from a very different angle, and that'll allow us to ideally do a radar shape model independently of any data that DART provides. And then we'll have an additional cross-check between the radar imaging and the inferences we make from that and the spacecraft data. Now, we can get the higher resolution radar imaging at closest approach, which is in March, but prior to the DART flyby, we'll be able to get the uncertainty down to plus or minus 12 kilometers. And again, the object's about 600 meters wide, so DART should be able to get quite close to CB21 and get very high resolution images during the flyby without any risk of collision. Now, I still have a bit of time on the clock, but this is all I can say with the data that we've got, so I'll stop and take any questions. Thank you.
Great. Are there any questions?
Just a comment that we have a pretty good solar phase angle on approach for DART, but we won't be getting much, if anything, from the backside. So radar's ability to complete the shape model for the part that we wouldn't be able to image anyways would be pretty valuable.
So is DART planning images only on the one side, or will they also turn around after the flyby?
We haven't made that decision yet.
Please talk in the microphone so the online can hear it.
I think they can hear me without the microphone, even online.
No.
But We haven't decided whether we're going to turn and look backwards at it, but it almost doesn't matter because it would be a crescent at that point. We don't have much.
And we have with the radar the advantage that we don't rely on the sun for our photons.
Yeah, we're not bringing our own photons either. So.
All right. There's a question over here. Fourth row.
Can you tell us how accurate you are in detecting velocity? 3 sigma? Roughly.
So, problem is we usually work this out in units of hertz, so I'd have to do the conversion in my head. But we've getting the Doppler shift measurements here to plus or minus about 1 hertz on the location of the center of mass. So the radar wave carrier frequency is 2.38 gigahertz. So whatever is 1 part in 2.4 billion of the speed of light.
Okay. Nice exercise.
Right. We have time for one more question.
I guess the uncertainty on your diameter comes mainly from the uncertainty in the pole solution, is that right?
The uncertainty here comes from our limited resolution. We can see that there's 4 echo bins that are visible, but plus or minus 75 meters is, in the radius, is our resolution limit.
Do you have a pole solution for this?
We do not have a good pole constraint beyond, we were not at high subradar latitude.
So can't you just get a lower limit on the diameter?
We can get a lower limit on the equatorial dimensions. We measure the visible range extent and derive a dimension from that, which is, again, 600 meters plus or minus.
Oh, I get it. Okay.
All right, can we thank our speaker one more time?
Okay, we move on to a talk by Yuri Medvedev of the Institute of Applied Astronomy in St. Petersburg, Russia, entitled Observations of Near-Earth Objects Using the 32-meter radio telescopes of the Quasar VLBI network.
Just a moment. Okay. Dear colleagues, I am Yuri Medvedev from Institute of Applied Astronomy. I want to say about a few words about our institute. Our institute have 3 astronomical observatories in Observatoria Svetlaya near St. Petersburg, Badari in the North Siberia, in the East Siberia, excuse me, in Zelenchukskaya and the North Caucasus. All observatories attached with a correlation center in the St. Petersburg and linked by optical fiber lines 10 gigabytes in seconds transfer rate. The main instruments of these observatories is 22 meters radio telescopes. Characteristic of these telescopes we can see this slide. The observation can be carried out both radiometric mode when the telescopes are working alone, and radio interferometric mode when the several telescopes operate in the net. Also, we have a new telescopes, 13 meters. We can see this specification of these telescopes. I repeat some information of radar observation. The radar observation allows us to obtain main information, position, object, size, shape, features of surface, and so on. Goldstone and Arecibo telescope provide the radar observation. We, from 25th, we have been carry out the radio observation of some object. The first asteroids that we observed 2011 was 2011 UW 1158. There's some information about this asteroid we can see in this slide. The absolute magnitude and approach distance allows us to receive radio echo from this asteroid by us telescopes. The signal, the Goldstone transmitted signal. Here I want to say thank you very much, our colleagues from Goldstone, the possibility providing their radio observations. We observed asteroids half an hour. Goldstone antenna transmit a circular polarization continuous wave. We used two separate canals to receive echoes in the same and opposite circular polarization. These figures present the power spectrum obtained in Zelenchukskaya and Badari. The solid line and dashed line denote oppositive circular and the same circular polarization. Also, we obtained a spin period of these asteroids. It was about 36 minutes. That's the value coincides with the light curve. Also, we estimated using the echoes bias with excuse me. And bias with we estimated polar silhouette. In this slide, we can see the change bias with the time and we obtained polar silhouette for the data obtained Zelenchukskaya and the red line and Badari black line. Means O minus C obtained by exactly orbits. Unfortunately, we can see that O minus C and are big. Now we try to correct this situation. Also, we now we go on to observe NEOS. Here we can see the spectra of asteroids 23 UTA1. For comparison, here also we can see echo power spectra asteroids 2011 UW 1158. In April, we received the radio echo from asteroids 2011, GQ25 and 23 BD45. Excuse me. In this slide, we can see we try to reconstruction shape asteroid from the radio imaging. And unfortunately, we do the first step in this way. In this slide, we can see solving the more simple problem, more simple task when we build radio imaging using known rotational model. Now we processing a phasor modulated signal for asteroid 2011 GO25. In short summary, our results confirm capability of static radar observation on NEOS. We plan to continue radar observation using obtaining continuous wave spectra and Regge Doppler image. Thank you so much for attention.
Thank you. Any questions? I don't see any. I have a question. Can you still use the Yevpatoria facility for radar work? Yevpatoria.
Yes, of course.
Is it in your?
No, unfortunately, up to now, we have not possibility to obtain signal from this observatory.
Okay. Do you have plans to do that in the future?
I hope that in the future we can to obtain something, reduce the best situation, and we can locate it by using this telescope.
Okay. Good. I think it's great that radar work is going international, that there is now another project that seems to be producing very good results outside of the United States. Okay. Any more questions? No, let's thank our speaker again.
All right. And now comes the last radar talk. And it's Marina Brozovic going to talk about Apophis. using Goldstone and Arecibo, and she's from JPL.
Approach of something of absolute magnitude of 19 or brighter that we know of in advance. Radar observations of Apophis started in January 2005, so this was just about 6 months after it was discovered at Kitt Peak. And Arecibo did these observations. There were also 2 additional times when Arecibo observed, and this was August in 2006, and then again in August of 2005 and May of 2006. At first sight, these data, and this is, by the way, everything that was collected at Arecibo at that time, they don't look like much. The Apophis is visible as this weak spike, maybe several units of standard deviation above the noise level in Doppler-only data. And then it was also discovered in delay in Doppler. It's completely unresolved. This pixel vertical dimension is 600 meters. So the entire asteroid fits within the single row of range pixels. And despite you not being able to resolve its shape, when you think about it, you are knowing the line of sight position of an object that is, at that time, was 30 million kilometers away. So this is a very powerful constraint on its orbit. And these 2 range measurements, and total of 5 Doppler-only measurements, they ended up uncovering bias in optical astrometry at the time. And as a result, the radar data showed that approach in 2029 is going to be 4.4 Earth radii closer to the Earth, but there was still no chance of impact. And another thing that happened because of these 5 measurements was that the volume of the statistical uncertainty space was reduced to 7% of its pre-radar value. And this brings us to our observations in 2012 and 2013. At this point, Apophis approached just under 1/10 of the AU, and this was the closest approach by this object after it was discovered and prior to 2029. It approached from the south, and at that time, at the time of the closest approach, it was outside Arecibo's declination window, but we were ready to observe it at Goldstone. And if I can get this animation to run. Oh, this is, no. Okay, here we go. So we started observing Apophis already in late December, and the movie is not playing. Excellent. So click it again. Okay, it doesn't matter. So basically, you would see how we started observing it in December and January, and then Arecibo started observing it in February when the asteroid was already moving away. Yes, and so you're going to see these little, yeah, this is actual Goldstone zapping it as it's going by, and then Arecibo starts a little bit later. So most of the data that we collected, this was at Goldstone. And this is where our strongest data come from. I'm showing here, these are the late Doppler images from Goldstone. And these are not your standard optical, plane of sky images. Radar images are very different. So on the vertical dimension, you have this distance from the radar. It's the depth, if you will. And then on a horizontal dimension, you have Doppler broadening due to object's rotation. And in a way, it's showing how fast parts of the asteroid are approaching toward you or away from you. And the vertical dimension of each of these panels is 900 meters. So I know what you're thinking. These are very, very weak, grainy images, and there are a lot of bright noise pixels. But you can start to get a glimpse of shape of Apophis. For example, you can clearly see that Apophis is an elongated object. And on January 3rd, we measured 450 meters visible extent, and then on January 9th, it was only about 170 meters. We knew that Apophis was elongated based on the light curves because they had a large amplitude, but what came as a surprise and what was not previously known is that on January 10th and January 14th images, we noticed this bifurcation in echo, and it's marked here with this white arrow. And this would imply that Apophis could be a contact binary. This would not be a surprise, because now we know that one every 6 asteroids in near-Earth population that is larger than 150 meters in equivalent diameter is a contact binary. And Arecibo and Apophis could be one of these. So what we usually do based on delayed Doppler images, we can invert them into spin and shapes of asteroids, but usually we're dealing with a much stronger data sets. But for the case of Apophis, we didn't have to start from scratch. There was already very strong model, both of spin and shape, from light curve data. This was published by Pravets et al. In 2006. You see that it is an elongated, this is a convex hull shape, it is an elongated object. The light curves also uncovered that it is in non-principal axis rotator, so it's tumbling. There are 2 periods here. So one is the period of precession around the angular momentum vector, and that is 30 hours. So if you look at the long axis going around light blue axis, which is angular momentum axis, this is 30 hours. And then if you look carefully, well, the green axis is with respect to angular momentum, you're going to see it banking like an airplane. It's kind of rocking back and forth. And this is the long period of 11 days. So starting with this spin and shape, we had 3 objectives. First of all, we wanted to establish the size of Apophis based on radar data, because remember, light curves can only tell you the shape, but they cannot tell you the size of the object. We also wanted to see if we could improve the spin state, and finally we wanted to improve the shape. So what I'm showing you here, this kind of jelly beans or slot machine, whichever one is your vice. So this is on the plane of sky how the Apophis would look like at the time of our observations, and this is the middle column is synthetic images that were produced by this model, and then the last column is data. And if you squint really hard, you see that the appearance of the echoes, they do resemble each other, and also the orientations of the echo look good. So that means the light curves did a good job with determining spin and shape. But if you zoom into these images on the January 10th and 14th, for which when we have, this is 19-meter pixel resolution, you can see that just a plain convex hull shape, the synthetic echo does not match the data, but if you introduce the contact binary shape, then this does resemble the data more. And we did some modifications to the spin state also to improve this. So, but I can talk about this offline. I would just like to quickly summarize what I just some of the highlights, and that is the equivalent diameters. We estimated that it's 340 meters. This one works the best, plus minus about 30 meters, and this number is right between the first published diameter for Apophis, which was about 270 meters by Delbo, and it's smaller than recent measurements, estimates based on thermal measurements by Mueller et al. And Licandro et al. With respect to radar albedo, Apophis is your kind of garden variety NEA. Its radar albedo is comparable to Eros, to Tatis, and Itokawa. With respect to optical albedo, so assuming that our size estimate is correct and that Pravets et al. Estimate of absolute magnitude is correct, we're getting optically bright object, and with still about 25% error bars. And this is just about, this is a little bit brighter than what was previously published, but just only by more than 1 sigma. So at the beginning of this talk, I mentioned what 2005 and 2006 astrometry did for Apophis orbit. So it moved it a little bit closer, the approach closer in 2029, so made us a little bit more nervous. But 2012 and 2013 astrometry ended up reducing the uncertainties for potential impact in 2036. There was a little keyhole there, and that made us feel a little bit safer. So in this plot, this is really a comparison of the previously published solution by Giorgini et al. In 2008 and difference between this new updated solution. So if you look here in a black curve, this is the differencing, and it's within 100 kilometer difference. And the good news is that difference between the old and new solution falls below statistical uncertainty of the old solution. So statistics works. And the news orbital solution has order of magnitude smaller uncertainties than the previous one. So all the way to 2029 flyby, we have less than 10 kilometers uncertainty of where Apophis is. And another thing that this new radar measurements did, they extended the predictability window. Now it goes from by 67 years. So it used to end at 2029. Now it's going all the way to 2058. As is, we do not have Yarkovsky detection yet. But in 2021, there's going to be another opportunity to observe this one. And it is entering Arecibo's declination window sooner. And therefore, the signal to noise is going to be about a factor of 3 stronger than in 2013. Here are the estimates of the signal to noise. So third week of March, it's going to be 150 units of standard deviation above the noise level. This should be sufficient for 15 to 30 meter resolution. This will hopefully is going to confirm the contact binary shape of Apophis. We can expect improvements in the spin state. With respect to Goldstone, the SNRs will be a factor of 2 weaker than what we had in 2013, but we can recover some of that if we receive a large antenna at Greenbank. Our predictions are that if the total position offset is of more than 12 kilometers is measured in 2020 apparition, this could signal Yarkovsky. And then if you have Yarkovsky, that means you can do mass estimate and bulk density estimate, which is important for any kind of mission planning. And radar astrometry in 2021 should extend the predictability window beyond 2059. 2029 approach doesn't look that far in the future anymore. Here I'm showing you asteroid approaching plus minus 3 days. This is lunar orbit. This is the geosats I picked up from NORAD, so you can just see how closely it gets. 20 degrees is vertical dimension. This is how large Earth is going to be on the plane of sky Apophis. This is ground track coming in, close approach Atlantic, and becoming a daytime object. So radar will be able to observe it both incoming and outgoing and see any kind of spin changes. Optical telescopes obviously will only be observing it during the close approach. And my last slide, just to show you how the orbit is going to change. This is again our incoming. The orbit is being bent, so the semi-major axis goes from just a little bit under 1 AU to over 1 AU, effectively reclassifying Apophis from Aten to Apollo type. And so this is it. Thank you for your time.
Well, that was worth waiting for, those animations. We have time for one question.
Very touristic question. Where should I go to see it? I want to see with my eyes an asteroid without telescope, or the only opportunity in history. From which place I should go? Because it looks like above Africa is already daytime, isn't it?
So, you want to see the close approach? Well, it should still be coming in a night sky. Well, how about cruise in mid-Atlantic?
Sorry?
How about, you mean in 2029?
Yes.
Mike, use the mic.
I'm sorry, are you taking 2029 approach?
2029, yes.
Well, as I said, how about cruise in mid-Atlantic?
Cruise in mid-Atlantic, okay, we'll book.
All right. Yeah. All right, Alan? And let's thank our speaker one more time.
Okay. We move on now from radar back to optical observations, I think. And this is a talk by Bill Ryan of the New Mexico Institute of Mining and Technology. That's the Magdalena Ridge Observatory. The title of the talk is The Physical Characterization of Near-Earth Asteroid 2012 TC4. We hope.
Okay, as indicated, I'm going to talk about the characterization of NEA 2012 TC4 with the 2.4 meter Magdalena Ridge telescope shown in the figure there. Okay, this is of interest mainly because there's going to be a close approach coming in the October 2017 apparition, where it's going to come to within about 60,000 kilometers of the Earth in terms of a nominal distance, maybe a little bit closer, maybe kind of closer to 1 lunar distance. Okay, this object is both on the JPL Sentry VI list and the ESA risk list. And most importantly this is a case where we have a close approach with this level of warning. Basically a close approach with the timescales of an astronomer's observing proposal season. Normally when we get an opportunity like this, we learned about it today, maybe yesterday, maybe the day before. This is a case where we have many months in advance. So we're anticipating extensive observing campaign from many observatories around the world. So this prompted us to go back and look at what did we actually learn when we looked at it as a target of opportunity back in 2012, right after it was discovered. So in that case, it passed a little bit further from the Earth, and it's also a little atypical of our target of opportunity system. We're usually doing NEOCP objects through the night, doing follow-up astrometry. When one of them turns out to be interesting, we'll take a break and then go get some light curve data, determine some spin rates, and then go back to our astrometric follow-up job. This is actually a case where we had some warning a couple days in advance. So we actually planned to observe this that night. So we looked at it a little bit longer and did a little bit more calibration data than we normally do. So the image to the right here is just an example of our photometric images. For this object, it was bright enough. We were taking somewhere between 5 and 10-second images, depending on where it was in the path, and able to get better than 1% photometry in those. We're also early enough before the closest approach that even though we're tracking on the asteroid itself, our field stars are hardly trailed at all. They still have close to arc-second point spread functions, even though they're a little bit trailed. So they're also sufficient for astrometric follow-up. Okay, so we plus Brian Warner, David Polishuk, Albino Carbignani, and a group of high school students from Massachusetts, we all generated composite light curves similar to what we see in the figure here. When I say composite light curve, what I'm talking about is the sequential time series photometric data folded with some identified period. In this case, we identified 0.2 hours, about a 12-minute period. And again, we all sort of generated curves that looked like this. Some of them, the error bars were a little bit bigger. The notable feature, aside from the rotation rate, was the fact that it was relatively high amplitude at about 0.9, looking at it as a simple rotation. We got a 0.9 magnitude amplitude, so indicated a relatively highly elongated object. Now, the thing that you'll actually look at is, if you look closely enough, you'll see that I am plotting error bars here. So just the error bars in most cases are smaller than the size of the plot symbol itself. So what we see is the fact that the spread in our data is an order of magnitude or more greater than our photometric error bars. So there is obviously something else going on. So going back and looking at the sequential light curves, what I'm looking at on the right-hand side is sort of sequential light curves from 2 different days that we observed this. And then on the left-hand side, I'm blowing up just the beginning portion here, just so you can sort of see what's going on. And so what we see is the very clear 12-minute periodicity, but there's obviously a second periodicity evident there. So we have an object that was in non-principal axis rotation. So when we looked at this in 2012, this was basically our goal. We were trying to identify spin rates as targets of opportunity as near as possible after they were discovered, and then we went on to the next project. So our goal was to try to help fill in the period versus H curve. And so this is the full curve of NEOs, and then this is the blown up left-hand portion of the curve, and then TC4 is this object right here. So it got a blue square because it's a tumbler, and it's a little bit slower rotator than something typical for its size, but it's by no means the slowest. So normally we try to determine quick spin rates, and then we'll do calibrations after the fact, usually using Sloan Digital Sky Survey data. I calibrate my comp fields that way. This was a case where we had actually planned this before the night started. Okay, so I did take some Landau calibrations this night, which again was atypical for what we were trying to achieve. One thing that it did, I just took 2 color data, so I was able to identify at least 1 color index. It was not very informative. It's just very average for a, very close to what I put in as my, if I don't know what the color index, the V minus R index is, I do something 0.42, 0.43. Okay, so the one thing this did, though, is allowed me to actually do our absolute calibrations a little bit better. And what we were able to do was determine mean magnitudes for the 2 nights that we observed it. One was at 25 degrees, one was at 30 degrees. Now, I put this plot up mainly because we were dealing with sort of a little bit of a mixed audience here, and we throw this value of H out a lot. Okay, this is somewhat of an absurd extrapolation. We saw some phase curves plotted earlier where these were filled in the whole way and the curve was identified. Okay, in this case, okay, I'm down in the linear region. I have 2 plots. What we do is we try to fit a nonlinear equation to this. That's again, I'm going to correct this. What we saw before was the 3-parameter phase curve. I'm looking back at the old 2-parameter phase curve. We just have a single H, a single G. Okay, we go through, we fit the curve where this line intercepts the y-axis. That's the H that's always plotted, and we've been hearing about in all of these talks. And then the G is related to both this curve and then the eventual linear slope. So realistically, I'd say what we could get from our 2 data points is just sort of a good estimate of the slope out in this region. So why that's important and useful to us, as Al Harris had pointed out years ago and has been studied extensively ever since, and these numbers have sort of changed over time. But what he has showed was the fact that there is a relationship between the slope parameter G, okay, and the taxonomic type, and then more importantly, there's a relationship between this slope parameter G and albedos itself. So what we're able to do is identify linear slope in this region. What I have calculated in the last problem, or the last column, is literally just mathematically what this value of G implies as a linear slope between these 2 phase angles. And what we find is the linear slope that I find in my plot is about 0.024, which is sort of exactly what we would expect for a bright E or V type of object. Now, the one thing I should point out that's not on the plot is these have error bars of about 0.003. So if you include the error bars of this, it kind of spills over into sort of a bright S type of object too. Okay, one other thing that we had at the time, we had a client who was actually doing some experiments of what could they do with a grading spectra. What that meant to us is we had a simple grading sitting in one of our filter wheels. We just tried, this object was bright enough, we tried to see what we could do. And I come up with a spectra that's plotted in blue here against the background of the typical S-mass range for Vs. Now, I would say that that's a nice match, except for the fact that this was a very crude setup. My confidence in these slopes, quantitatively, I would not put as high. What I am relatively confident of, though, is the qualitative shape. We're clearly not looking at a dark object. Okay, so finally, in summary, what we have is the fact that when we look at the MPC data, which tends to have photometric accuracies of 0.0 or 0.1 magnitude at best. They tend to be a couple tenths of a magnitude. Okay, the MPC estimate of the H value is 26.7. From this work, we point out that it's a little bit lower. I have a healthy error bar on here, but more importantly, we're looking at something, I think, with a relatively high albedo. So what that implies is we have something that's going to be on the order of 10 meters. So if we look at the size estimates we get from the MPC, what we're claiming that we've kind of narrowed it down to sort of the smaller size end of that. That being said, this is not a perfect sphere. This is a highly elongated object. And then ultimately, I'm putting this out here, and unfortunately, I'm going to get either proven right or wrong in the coming months. Okay. What our particular interest, though, is to actually look at the fact that we have some high-resolution light curve data from 2012. That was pre-close approach in the last apparition. So what we would like to do is see what kind of changes what possible changes occurred in the rotational state from the 2012 close approach, because this year we're actually going to be able to observe it optically before the close approach. Okay, and then my last slide, based on the talks yesterday, is not quite as important. Tim already pointed out that 10 meters triggers an IWAN alert, so I didn't need to highlight that part. Okay, thank you.
Right. Any questions? I have a question. Let's assume you do see changes in the rotational state. What will that tell you? What information are you hoping to get out of that here?
Well, looking at it as a single period like her, we see even in that we have a high amplitude. So we know that we have an elongated object. So what we would see in this is the fact that something with that shape approaching to within a quarter of a lunar distance, that's close enough for it to actually experience torques that can affect its rotation state. That's the best answer I can give you right now.
Okay. I'm just wondering what sort of higher level information about asteroids can one derive from that sort of observation? A change in rotation state through a close approach.
The change in, that's to a degree, that's going to give us information as to, during close approaches, objects of different shapes, how realistic are models that they're going to experience changes in the rotation state and then possibly,
Okay, so one possibility is, for instance, if it's spun up, that I think is one way you can produce a binary, for instance.
Yeah, I'm not expecting that from a single pass.
No.
But yeah,
okay.
Yeah.
Right, fair enough. Any other questions? Oh, yeah.
Will it be observed by radar as well?
Yes. I'm speaking for someone else, but.
So uncertainties on TC4 orbit are still really large. Currently, the close approach is occurring somewhere off the coast of Antarctica. So yes, we should be able to observe it. We have periods when we can observe it with radar, but the orbit can still be it's highly uncertain. So we'll have to update you exactly on when afterwards. And currently, Goldstone is the only one that can observe it. Arecibo, no. But if the orbit changes, maybe Arecibo will be able to observe it too.
Okay, let's thank our speaker again.
All right. And our next talk is Alan Harris, talking about the relevance of thermal inertia for planetary defense.
Great, thank you. Okay, thermal inertia, what is it? We've got two asteroids here. This one has low thermal inertia. Microphone. This one has low thermal inertia. That means, for instance, a dusty regolith, a moon-like regolith, it means that the solar radiation does not, or the solar energy does not penetrate far into the surface. You have a prominent subsolar maximum in temperature. On the night side, that small amount of energy is radiated away very quickly. The surface cools down. You have a cold surface on the night side. If you have an asteroid, on the other hand, with high thermal inertia, it means that on the surface you have material with a higher density, higher thermal conductivity. Note the definition of thermal inertia here. That means that the temperature on the day side is lower because energy, radiation, or the thermal energy from the sun is conducted into the asteroid, and it takes a longer time to come out. It's conducted deeper into the surface, and therefore on the night side that energy comes out again, and the asteroid does not cool down quite as much on the night side. So thermal inertia makes a big difference to the temperature distribution around the asteroid, and that is what you can measure or sense with a thermal infrared telescope. Let's see if we can move on. Yeah. So what is the relevance then of thermal inertia to planetary defense? There are three things I could think of. One, the Yarkovsky effect. That depends on thermal inertia. So if you can work out the thermal inertia of an asteroid, for instance, a potentially hazardous asteroid, you can then better estimate the effects that Yarkovsky will have on the orbit of that object. If you can determine that your asteroid has a high metal content, for instance, or sorry, if you can determine the thermal inertia of your asteroid and it's high, that might suggest that you have high metal content. If the asteroid is coming at you, you would want to know that because it could create a lot more damage if it was a metallic object, a dense object, than something else. And finally, what I'm going to show here is that thermal inertia can provide insight into surface structure. So, the observational data that we've been using for this study, I should point out indeed that it is a NEOShield-2 study. So this work has been done with funding from the European Commission, the Horizon 2020 program, in particular the project NEOShield-2. We can use observations from a number of telescopes. We have data from Keck, from Spitzer, from IRAS as well indeed, and other telescopes. In particular, in this case, I've written WISE rather big here because most of the data that I'm talking about here comes from the WISE project. So the usual way to determine thermal inertia, the thermal inertia of an asteroid, and the most accurate method is to do what we call thermophysical modeling. And this is a rather sophisticated process of taking a shape model of an asteroid, the more accurate the better of course, and having a whole load of observations taken at different solar phase angles and different aspect angles. And if you've got all that and sophisticated software, you can calculate thermal inertia and other things from your thermophysical model. It is a very difficult procedure, and we only have enough observational data to do this on relatively few asteroids, namely about 50. And that those asteroids have been conveniently tabulated in this chapter by Delbo et al. In Asteroids 4. And I think we have fairly reliable thermal inertia values for about 50 asteroids. So the question we asked ourselves was, is there a shortcut? Do we have to go through this complex procedure to determine thermal inertia, or can we sort of estimate it in a sort of quick and dirty way? And we've come up with a quick and dirty way using simple thermal modeling. I should have pointed out, yeah, the spherical asteroids, of course, don't exist, but this sort of simple model can be very useful, in particular for determining diameters and albedos. What you do is you basically equate the energy going into the asteroid with the energy being radiated out as thermal energy. If you don't have instantaneous thermal equilibrium, which you normally don't have, then you can put this factor eta in to balance things out. And by playing around with values of eta, you move these curves around until you find one that fits the observational data, in this case the dotted curve, and that fixes your value of eta. And it turns out that eta, of course, as you can see here, carries information on a number of things, but in particular thermal inertia. So we asked ourselves, could we use values of eta? And they are very conveniently tabulated in the WISE data set in a number of publications. Can we use those data to actually give us an estimate of thermal inertia? And we did, I'm missing out lots of stuff here because I haven't got enough time, but we came up with this expression. If you go back to the work of John Spencer back about 1990 or so and work through all that sort of thing, you can come up with this expression basically because the thermal parameter that he derived or defined is related to the eta value. And so you can actually you can relate thermal inertia to the eta value, which comes out of the simple thermal modeling. Anyway, this expression looks very simple compared to all the effort that goes into thermophysical modeling. We asked ourselves, can this really be true? Does it work? And how accurate if it is it if it does work? Now, the details I'm missing out, you can get out of this publication that came out in December last year. But what we did, we sort of, first of all, tried to determine how well we were doing with this. So we plotted values of thermal inertia that we derived through our little estimator based on the values of eta, with those values tabulated in the chapter by Delbo et al. In Asteroids 4, derived from thermophysical modeling. And I think you can see here that it's not that bad, is it? I mean, it's a log-log plot, beware, okay, but we're going through the entire solar system here. We're going through from NEOs right through to TNOs, and basically we find that the RMS fractional deviation is 40%. So with our crude estimator, we seem to be getting thermal inertia values down to about a factor of 2, to within a factor of 2. And so I think that's reasonably good agreement, given the, I mean, the error bars even on the thermophysical modeling are pretty enormous. So I think so far so good. And we then suddenly, with this little expression, we could calculate thermal inertia values for about 500 or 600 asteroids instead of just the 50 that we had previously from thermophysical modeling. So it was like a new toy. It was like Christmas, you know, and you play around with it. And we tried plotting thermal inertia against all sorts of things. And I thought, well, I was still a bit concerned that this expression was a bit bogus and wasn't giving us the right result. And I thought, well, I'm going to plot it against a parameter where I do not expect to find any correlation at all. It should be just flat. So I came up and I thought, right, rotation rate. Why should thermal inertia depend on rotation rate? Pff, no reason. However, I reckon that's the correlation. And it seems that thermal inertia, gamma here, in SI units, is increasing with rotation period. The slower an asteroid rotates, the higher the thermal inertia value that we're seeing from the WISE observations. This is for main-body asteroids. The red points are the thermophysically derived data from Delbo et al. And you can see that those points alone do not really, you can't say that there is a trend of increasing thermal inertia with rotation period from the red points alone. If you take the black points, which down here seem to occupy the same region of the plot, it looks as though it's fairly consistent, but the black points, which are our estimated thermal inertia values, go upwards. Notice that we're dealing with only main-belt asteroids here. The median diameter is 24 kilometers. And we thought, what about near-Earth objects? Okay, so we went back to the chapter by Delbo in Asteroids 4 and found out that there are enough NEOs in that data set that we could simply use the published values of thermal inertia based on thermophysical modeling, not using our own estimator. And when we did that, lo and behold, you find a similar correlation. So this gave us a lot more confidence that the correlation of thermal inertia with increasing rotation period is real, because this does not depend upon our crude estimator. These are thermophysically modeled values of thermal inertia. So yes, it does seem that this relation holds for NEOs. One could sort of tend to assume that it holds for all asteroids, anywhere. What's the explanation for this? Why should thermal inertia increase with rotation period? The answer, we think, is the fact that what is happening here with higher thermal inertia, solar energy is penetrating deeper into the asteroid. As you go down through the top surface layer, you're going down through the porous layer, through the dust, down to material which has a higher density and a higher thermal conductivity. You're underneath the top porous dust layer, you've got grit and then gravel, and we reckon that these data are telling us, for instance, if you take the red points here, these are main belt asteroids, assuming a density of 3,000 kilograms per cubic meter, and the black points are the near-Earth objects, okay, with the black points with the arrow bars are near-Earth objects. The lines here are these are not fits, they're just lines for guidance for the eye. The blue points assume a lower density of 1,000 here. And it seems that as you go, this is skin depth, this is the depth to which the diurnal thermal wave penetrates. So and as you go down into the asteroid, the thermal inertia goes up. And you can see here that extrapolating upwards, we're going to hit the thermal inertia value for solid rock, in the case of main belt asteroids, within a few meters of depth below the surface. In the case of the near-Earth asteroids, it's a little bit steeper, and it looks as though extrapolating upwards that you're going to hit solid rock within a few tens of centimeters. Now, solid rock does not mean a sort of platform of rock. We're talking about sort of fist-sized chunks of rock below the surface. Now, we threw caution, even more caution to the wind, and we decided we'd restricted ourselves to that point to objects for which we have spin vector solutions. So we could work out the angle between the spin axis and the sun. And you need to do that for the modeling. And so we found out that there was many objects have solar aspect angles that are pretty well not too far from 90 degrees, as it turns out. So we took the median value of 65, the sign of that is 0.91, and we then had a lot more points that we could use, even though you have to take this with a pinch of salt, because we are making a big assumption here. But you can see, if I flip back here, you can see that the story is the same, that even with these high number of points, the trend is the same. The green points are near-Earth asteroids, and we're heading up towards solid rock here within a few tens of centimeters in the case of near-Earth asteroids. One other thing we did was to look for correlations of thermal inertia with taxonomic types, and I think you'll agree that the blue points, which represent M-type asteroids, have in general a higher thermal inertia than the P's and the D types, which you'd expect, of course, if M types contain more metal. And finally, the conclusions, and I'm finishing here. Thank you. Any questions? We interpret our discovery in terms of rapidly increasing material density and thermal conductivity with depth. The impact on, or the relevance for the planetary defense is the Yarkovsky effect. You need to know thermal inertia. You're going to want to know the rotation rate of your asteroid to calculate the effects of Yarkovsky accurately. Now, imagine the kinetic impact of spacecraft coming in. If you have solid rock just a few tens of centimeters below the surface, you're going to have more mass being ejected. And so the kinetic impact will be more efficient, the beta factor will be higher on the basis of these results. I'd like to see some thermophysical modeling carried out on slow rotating asteroids to back this up so that we can have even more confidence in our results. Thank you very much.
All right, I think we have time for one question. Yeah.
Alan, did you decorrelate your thermal inertia data for temperature effects from the distance to the sun? Basically, it's
it's a 1/r dependence of thermal inertia to heliocentric distance because of temperature effects on heat capacity and also on conductivity, especially for higher thermal inertia where you have larger grains and radiative conductivity dominating.
Well, of course, the thermal inertia, yes, you're right. There is a correlation in the sense that objects nearer the sun have a higher thermal inertia. Objects further away have a lower thermal inertia. I mean, our equation will take that into account. And that would only be a problem if there was some correlation between distance and rotation rate, for instance, which we don't see.
I can't see that, but maybe if you scale that to the same mean temperature, so the scatter gets just smaller.
Oh, I see. That's possible. Yeah, yeah. That we didn't do that, but it could indeed reduce the scatter. Although we're talking about, on the one hand, the main bud asteroids all occupy roughly the same region in space from the point of view of the thermal inertia. You only get a big difference if you go from NEOs to main belt to Trojans to TNOs. Then you see the difference very clearly, as you saw on the log plot I showed. Yeah.
Okay. Yes.
There's Andy up there. He's screaming to ask a question.
Andy, but it's going to be the last one. Yeah.
I know.
Yeah. So.
One last question.
Okay, really interesting as always. I'm wondering if cause and effect could be reversed in some way as well, because people have proposed that thermal cycling in asteroid surfaces might create regolith. So whether faster rotation means that you cycle faster, so you make finer regolith. So your thermal inertia goes down for the faster rotators.
That might contribute to it, but I think, by looking at the skin depth, you see, it seems to me that is the primary effect. But I guess that could also be a contributory factor. Yeah, I have to think. Yes, we can talk.
But this effect doesn't. You can actually see the effect on the first. What is it? When do we start seeing the effect?
After 10 hours.
After 10 hours, yeah. So you don't see it for the faster rotator at all. All right, but we have to move on.
Yeah.
All right. So the next speaker is Makoto. Oh, sorry. Yeah. Yes, the next speaker is Makoto Yoshikawa from JAXA, results on Hayabusa and Hayabusa 2.
Oh, okay, thank you very much. Yes. Okay, so I'm going to talk about the Hayabusa and the Hayabusa 2 result. And these are co-authors, but of course, there are lots of people who are working for the Hayabusa and Hayabusa 2. Okay. Okay, so this slide shows the history of asteroid from molecular cloud to the present. And by Hayabusa and Hayabusa 2, we want to study from protoplanetary disk to asteroid. There are lots of processes, and we want to know what happened in this period. Okay, so this is Hayabusa mission, and I already talked yesterday, so I skip this. Anyway, Hayabusa, the mission period was 7 years. And yes, this is Hayabusa spacecraft, very small. Dry mass is just 308 kilograms. And it has these remote sensing instruments. First one is Amica. This is a CCD camera. And the next one is LiDAR to measure the distance between spacecraft and the asteroid. And NEOS, this is a near-infrared spectrometer. And finally, XRS, this is a X-ray fluorescence spectrometer. So Hayabusa had these 4 instruments for science. And you have seen many times, this is Itokawa, okay? And this is also Itokawa. This is a sample that we got, very tiny. So this is a sample, but this is 100 micron, 0.1 millimeter, very small. but we can cut such small sample like this, and we are able to analyze these small particles. And for example, I show you this photo. There are many features. We found many features in such a small particle. And from this, we can analyze what happened when Itokawa evolved. So this summarizes what we learned from Itokawa. Of course, we estimate mass, and we have shape and volume. Then we can calculate density. Its density was 1.9 gram per cubic centimeter. And of course, we had a sample from Itokawa. So we know Itokawa is consist of ordinary chondrite. Its density is about 3.2 gram per cubic centimeter. So simple calculation, macro porosity is 40%. So that's why we concluded that the structure of Itokawa is something like this, rubber pile structure. Okay, so this is a very important result from Hayabusa mission. And also we study space weathering. We had lots of data related to the space weathering. And this is a history of Itokawa that we estimated. So 4.5 billion years ago, planetesimal were formed. And we estimated the size is about 20 kilometers or larger in diameter. This size comes from the temperature. From these samples, we found that the original temperature of original body became much higher than 800 degrees. So that's why we estimate the size is much larger than 20 kilometers in diameter. And then 1.3 billion years ago, some catastrophic event occurred, and Itokawa was formed. And later, this is a space weathering. Okay, so such scenario we were able to estimate. So yes, this is the same chart, so I skip this. And the next mission is Hayabusa 2. So Hayabusa 2 is quite similar mission to with the Hayabusa, original Hayabusa, but we have a new challenge, that is this one. We will create a new crater on the surface of Ryugu. And I think tomorrow, Dr. Tsuda will talk about Hayabusa 2 mission, so he will talk about this in detail. Anyway, this is a spacecraft, Hayabusa 2. It is quite similar to original Hayabusa, but there are many instruments. These are scientific instruments. I will talk this later. And there are 4 rovers and landers. One is mascot by DLR and CNES, and the other 3 are small rovers, Minerva 2. So actually, Hayabusa 2 has a lot of separable payloads, so just this one. So these instruments will separate from Hayabusa. Okay, so this is orbit. So after launch was 2014. For first 1 year, Hayabusa 2 were moved like this along the orbit of Earth. And then in 2015, December, Earth Flyby took place, and the orbit changed like this. Okay. And Hayabusa 2 has these 4 science instruments. It is similar to Hayabusa, but a little bit different. One is optical camera, and the next one is LiDAR. So these 2 are similar to original Hayabusa. And the third one, this is a near-infrared spectrometer, but the spectral range is different. In this case, we take we get the data around 3 micron. And finally, this is a thermal infrared imager to measure the temperature of the surface of Ryugu. So in this chart, there is in detail things are written. So if you have interested, please look at this later. So using these many instruments, we can study science for wide scale range. Large, this is a scale, and from large scale to micron scale. So these are instruments, and these are Land and Rover. And Mascot has 4 science instruments. So like this, we can study Ryugu in detail. Okay, so this is Earth by, but maybe I should skip. I think Tsuda-san will talk about this tomorrow. But just show you, this is a photo of Earth just before Hayabusa 2 approached to the Earth. So this is by wide angle camera. Also, we have such a photo. This is a very beautiful photo of the Earth by narrow angle camera of Hayabusa 2. And this is the Earth. This is the Earth by thermal imager, like this. And also, we checked NEOS 3 near-infrared spectrometer, and also we had an experiment of LiDAR. Okay, so the target asteroid of Hayabusa 2 is 1999 JU3. Now we call Ryugu, and these are current data. The shape is something like this, and size is about 900 meters in diameter. And this is a typical C-type asteroid, and the rotational period is about 7.6 hours. And recently, there are several new papers like this. This is by Miura, and the effective diameter is something like this. And the spin axis is also estimated like this. And this is the spectrum data by Permna et al. Okay, so of course, we don't have any result for Hayabusa 2 mission, so result will come next year. Okay, so just summary. Hayabusa were able to reveal the nature of Itokawa, small S-type NEO. So this result contribute to the work of planetary defense. And next is Ryugu. And this is a small C-type NEO. So currently, up to now, the Hayabusa 2 is a very nice status, and it will arrive at Ryugu next year in June or July. So now we know Itoka quite well, but next year we will know the we will know the Ryugu in detail. So this is a big model of Ryugu in JAXA. Okay, so thank you very much for your kind attention.
Thank you. Are there any questions? Any questions? All right.
Just a stupid question. What will be the target of Hayabusa 3?
Okay. Now, we don't say Hayabusa 3, but in JAXA, we are discussing next mission of, for asteroid. One is the Jupiter-Trojan, and the other one is Phaeton Flyby mission.
Phaeton?
Phaeton, yes, right.
Great. Look forward to that. Okay, let's thank our speaker again. And the next talk is excuse me, by Yun Zhang of the School of Aerospace Engineering, Tsinghua University, Beijing. And the title is The Cohesive Strength of 65803 Didymos, the Target of the AIDA Mission. Thank you.
Thank you very much.
Good morning, everyone. I would like to present our recent research on characterizing the physical property of the AIDA mission's target, Didymos. So, as some of you may be familiar with, the AIDA mission will be the first kinetic impactor experiments carried out at real asteroid scales. Through this mission, a better understanding of the physical properties of this Didymos system is expected to be achieved. But based on the current observations, the only certain things about this Didymos system is the spin period of its primary. As shown in this table, there is a big uncertainties on its size, mass, and bulk density. Using the nominal value of these properties, the slope analysis of its the primary shape show that most of its surface area is subject to very high shear stress. The primary could be driven by the yaw spin-up effect in the past, so its spin rate is increased to close to its fastest spin limit by now. If the friction angle of the primary's material is close to the dry sand on the Earth, the primary cannot hold its current shape at a spin period of 2.26 hours. So, current observed systems show a very unsteady. But since there is a big uncertainties on its properties, we can assume that the primary is stable and put some constraint on these properties. For example, increasing the bulk density or adding cohesion into its material will both improve its structural stabilities. Consider that these two properties will also affect the performance of the AIDA mission. So to support this mission, we explore the plausible bulk density and cohesion of the Didymos system in this study. We used the Medvedev PKD graph to carry out this study. The primary is assumed to be a self-gravitating RoboPie like this. The rotational and the motion of these particles are solved by the equation listed here. And we model the yaw spin-up effect by artificially decreasing the spin period of the simulated body in a manner like this. And we check the stress state variables, the parking efficiency, the shape, and the contact numbers of this simulated body during the spin-up process. By checking the Krebs deformation of the simulated body during the spin-up process, we can obtain the spin period where the body becomes unstable, and that is the spin limit for this simulated body. So, correspondingly, use the same method by carrying out a series of simulations with various conditions. We can get the properties of the body, which can make it to be exactly stable at the current observed spin period of 2.26 hours. Here I present our results as a nominal bulk density case for 3 different configurations: the hexagonal close packing, and the random mono dispersed packing, and the random poorly dispersed packing. With the same setup, you will see these 3 models distributed at different spin period. As shown in this movie, the random mono dispersed packing distributed first, and then it's the poorly dispersed packing. The hexagonal close packing can keep a stable shape at an even higher spin rate. So our study showed that the configuration of the RoboPie will have a big impact on its structural stability. And our recent published paper discussed the correlation between the configuration and the failure behavior of RoboPie in detail. But for the purpose of this study to explore the properties of the Didymos primary, clearly none of the I showing the 3 configuration can be stable at a nominal bulk density of 2.26 hours of 2.1 gram per cc. But consider that the Didymos primary has a big uncertainty on its bulk density. So a stable structure will be possible if its bulk density is higher. So we explore the model for higher density and get the critical bulk density for these three models. With this value, the three model can be exactly stable at the current observed spin period. And there, as shown here, the hexagonal packing and random poly dispersed packing can be stable within the observed measurement uncertainties. And their grand density also reasonable for an S-type asteroid, as Didymos did. So from our study show that the primary could be stable within the measurement uncertainty of its bulk density. So maybe no cohesion is needed. But if the current observed nominal bulk density is real, there must be some cohesion in the primary's material. So to explore the effect of the cohesion, we implement a cohesive force model in PKT graph. Among the physical source of cohesion in asteroids, the van der Waals force could be the dominant force. The cohesion strength arising from the van der Waals force for the micro-sized grains could be as high as 10,000 Pascal. And this interstitial micro-sized grains could provide a significant cohesion between these meter-sized borders. So the whole RoboPy could be cohesive. So based on this granular branch idea, we propose our cohesive force models. We use the shape parameter to characterize the size of the contact area that can transmit the cohesive strength, and use the interparticle cohesive tensile strength to reflect the physical properties of the interstitial regulus. By adjusting the interparticle cohesive tensile strength, we can simulate a lot of range of cohesion material. So we applied our cohesive model to study the cohesive strength of the Didymos primary. Instead of use the spin-up procedure as we used for the cohesionless case before, we keep the spin period of the simulated body constant as this 2.26 hours. And we decrease the interparticle cohesive strength by a certain amount at every time interval. And we check the creep stability of the simulated body at every time interval to see if the body can stable at that cohesive strength. So we take the hexagonal packing as a study case. We use 2 stages to narrow the critical value of C into 10 Pascal. So this figure shows the evolution of the shape, packing efficiency, and contact number of the simulated body during the second cohesion test. And the green rectangle shows the stable case, and the red one shows the unstable case. In the stable case, it shows that the shape and packing efficiency can be stably vibrate around the equilibrium points. And in an unstable case, the packing efficiency and the contact number will continuously decrease. So the creep deformation occurs in this case. The body becomes unstable. So by this means, we can identify the critical interparticle cohesive strength for the hexagonal packing is 140 Pascal. As shown in this movie, as C decreases, the body will disrupt eventually. And compared to the cohesionless case, you can see that the failure behavior is quite different, and the failure condition is also very different. So our studies show that a small amount of cohesion can significantly improve the structural strength of a RoboPy asteroid and change its failure behavior. Since the dynamic behavior of a granular assembling is related to the interaction of individual particles. So we try to explain the effect of cohesion by analyzing the force chain distributions. This figure visualizes the normal contact force distribution of this hexagonal packing for a different cohesion strengths. The blue strengths show the cohesive strengths. So it's clear to see that as C decrease, cracks initiate in the surface. And to reveal the internal distribution of force chain, we choose 2 slides to reveal their distribution. As shown in these figures, most of the cohesive force chains are parallel to the horizontal plane, as shown here, which is also the best direction to offset the centrifugal force due to the rapid rotations. And as shown here, it's clear to see that cracks initiate even when the cohesion is pretty higher. An explanation for this is that the strong cohesion motivates the formation of agglomerates. So as shown here, the surface particles are well connected to the particles beneath them. So the centrifugal force act on the surface particle will also pull the subsurface particle who has connection outward. And the surface and subsurface particle will work together to pull the more internal particles outward until cracks occurs to cut off the process of agglomerations. So that's, since the spin period of this body is pretty high, this agglomeration process can propagate to the center region, so cracks initiate near the center. So as shown here, the whole structure is no longer homogeneous, and these resulting agglomerates will behave like a solid material. And these figures are colored by the magnitude of the tangential contact force. As shown here, it's clear to see that the cracks between these agglomerates carry the highest tangential contact force, which will block their relative slack motion and make the structure become stable. And as shown here, as the C decrease, because the innermost particle of each agglomerate carries the highest cumulative centrifugal force. So the internal cohesive connection will break first. So that's why these show here, they will break from the inside out. So from the above study, we obtained the critical value of the interparticle cohesive strength for the hexagonal cross-packing. But this is not the cohesive strength we usually use when we're talking about the granular material. Normally, the cohesive strength for a granular material is defined as the shear stress at zero pressure. So as shown in the Moore Coulomb failure criterion. So we name this big C as the microscopic cohesive strength. And by carrying out the stress analysis of the simulated body at its limit failure state, we can obtain the value of cohesive strength and the friction angle for this body. So from our study, we showed that the hexagonal packing can be stable with a cohesive strength of 6 to 6.5 Pascal as a nominal bulk density. So in this study, we investigated the possible properties of the Didymos primary, which can keep its shape stable. And we showed that when the cohesion is not included, density higher than 2.4 grams per cc is needed. Otherwise, the cohesion of 6.5 Pascal is necessary to maintain the shape stability at the nominal bulk density. Thank you very much.
Thank you. One very quick question. Boris.
Do you expect the same cohesion for the secondary?
Do you expect the same cohesion for the secondary?
Maybe not, because as shown in our study, the configuration will have a big impact on this structural stability. So if the secondary is formed by the primary, it may have different distribution as the primary. So maybe there is different cohesions inside.
Okay, let's thank our speaker again.
Thank you.
All right, and the next speaker is Oliver Barnouin, and he's going to talk about assessment of asteroid shape produced after catastrophic disruption. And he's from Johns Hopkins.
Yeah, thank you. Just on Yun's talk, that cohesion is probably a low-end member, so if she goes to a random packing, it'll go up a little bit, but that number is kind of in the realm of the right place. Today I'm going to talk about the origins of top-shaped asteroids such as Didymos, but looking at primarily formation of such shapes through reaccumulation after disruption. Now, we know that Yorp is usually attributed to most top-shaped asteroids like I'm showing here, and there's good observational based statistical arguments for why. But several people have proposed that some of these shapes do not necessarily all have to be the result of Yorp spin-up and reaccumulation. I'm going to focus on the formation of these types of shapes of asteroids through reaccumulation. I'll talk about this in a second. And really the point is, can we learn anything about the possible physical properties of something like Didymos if it was product of disruption and reaccumulation? So what we did here is we looked at, we used some catastrophic disruption simulations from a range of impact conditions. These were actually produced originally by Patrick Michel and Martin Jutzi in a paper they published about 4 or 5 years ago. They varied the radius of the target. They had variable porosities. They varied the impact velocities. They changed the mass and the impact angle, but they basically always looked at targets along the Q star line, so everything was being fully disrupted. Q star, for those who don't know, is basically the ratio, is the threshold at which a mass of more than half of an asteroid is disrupted. We also used for these simulations a strength parameter, which were basically derived from laboratory experiments for objects of 1 centimeter in radius, and also by using spin-limited data. These are all from whole sample, and we actually varied the range a little bit around this 6 to 10 to the 7 Pascal, 10 to the 8 as well. Okay. So as I said, we used the Jutzi and Michel results. They included porous models for porosity. Hopefully this movie will play. See if I can get it to go, yeah. This is actually an example of one of the simulations that Michel and Richardson looked at and forms a kind of Itokawa-shaped object. And so these are the kinds of results we used. We also used the same code that Yun just talked about, PKD grav, except we're not using the soft sphere part of that code. We're using the hard sphere part. That's mainly for numerical reasons so that we can get solutions fairly quickly for the formation of these objects. In those hard spheres, we do sort of simulate in some way how things sort of stick together as they reaccrete. When we have low force collisions, the particles can actually stick together, sort of representing a sort of cohesionness between the particles. If there's moderate collisions, then the forces are strong. The collision between the bouncing balls are big enough so that they can actually disrupt again, and or bounce, and then finally they'll disrupt again.
And the strength is adjusted to the measured strength, again, of the materials in the lab. Once we take after that, we take the results of these simulations, and then we actually then go ahead and take any reaccumulated aggregates that are greater than 10 particles and compute their center of mass, find their principal axis of rotation, fit an ellipsoid to them, and get basically a semi-major semi-major and minor axes. And then we systematically assess the influence of different impact conditions and target properties on the resulting shapes. I'm going to step you through sort of an example here. This is a case where we have a projectile coming at 4 kilometers per second, so hitting a 10-kilometer object. The projectile here, I think, is 13 kilometers. The impact angle here, this is actually an incidence angle, is of 15 degrees, so it's nearly vertical. The porosity is 50, and the strength is this for that simulation. And this is sort of the output of some of those kinds of models that we generate from that impact. We then plot these results in a graph like this, the ratio of the semi-minor, the two semi-minor axes relative to the semi-major axis, just so you can sort of understand what I'm talking about. So A is along this side, B is this side, and C is this. And to bound the problem, I've sort of put Didymos, KW4, and Bennu on sort of one end, which are sort of the typical top-shaped objects. And on the other end are very elongated objects. In fact, Eros is probably one of the most elongated objects that we've seen on the other end. And then this plot sort of shows you the distribution of aggregates that we get for that one simulation. And you can sort of see that the top-shaped asteroids up here and the Itokawa-shaped asteroids sort of bound the distribution of things that we get. And when we start looking at the occurrence of these bodies, so again, Itokawa in this area, Didymos down here, you can see that objects such as Itokawa and Eros are fairly difficult to make. You start approaching top-shaped asteroids, those can be formed. Oh, the other thing that I've put in these plots is you might notice these circles. That's actually the sort of mean and standard deviation of the distribution. Okay, so the first thing I want to do now is go through and address how strength effects might change the distribution of the particles that you get. Okay, the distribution of the sizes of the particles or aggregates that you get. So here I've increased the strength, so we just imagine increasing strength across here. And what you find is that the distributions actually start slightly, well, they don't actually vary a whole lot, but you do see a greater generation of more and more top-shaped asteroids. So strength seems to push you towards making more of these Didymos and KW4 objects. So that's one thing. While down here, you're still sort of in a fairly uncommon regime with the Itokawa and Eros models. When you start looking at the effects of impact angle, this is basically you're adding more angular momentum to the system. What you actually see is that you reduce the likelihood to form top-shaped asteroids. You're noticing all these spots, and actually the mean is also moved down quite a lot as you go from near vertical impacts to fairly oblique impacts of about 45 degrees. This is actually probably the most common type of impact angle you would get between two objects. You also are starting to see some evidence that you can get down to these more elongated objects. When you decrease impact velocity but maintain Q star similar, you can play that game because Q star is not independent of impact psi of projectile source of velocity. Those two are combined. You don't really see a lot of differences between the scenarios. The distributions are more or less the same, at least statistically speaking. So that was interesting. What happens when you do introduce porosity, however, is that we are seeing that increasing porosity will actually tend to move your distributions to higher numbers. You definitely see the presence of more top-shaped like asteroids, and actually a decrease again of these more cigar-shaped Itokawa and Eros-shaped asteroids. So porosity seems to play a big role here. So my talk's much faster than Yun's. The preliminary assessment of looking at the different shapes of asteroids is that resulting from disruption is that most aggregates actually are formed around with semi-major to semi-minor axes that are about around 0.82 to 0.7. So that's where the bulk of the populations would be. Top-shaped and cigar-shaped, which tend to bound the problem, are less commonly formed. But I would say that top-shapes are more common than cigar-shaped from reaccumulation. The additional findings is that yes, we tend to get more top-shaped asteroids when you have a parent body whose porosity is large, when you have a little bit more cohesiveness or stickiness, and that the projectile parent body plays a big role on this. If you have a more oblique impact, you tend to actually generate more top-shaped objects. So the ultimate goal was actually to support the DART mission. And so the implication for Didymos and its secondary is that we might be dealing with, if this is an asteroid that's the product of impact disruption, it's a more porous target, it's more likely to have cohesive aggregates, and it was probably the product of a low obliquity impact. So that's all I have to say about this. Thank you. Questions?
Anyone? Yeah? Oh, sorry.
There's somebody in the top there
yeah.
who just...
I don't know if I can speak loud enough, but did you look at the range of top shapes and cigar shapes as a function of spectroscopic type?
Not in this study. I don't know how we would be able to do that in terms of the numerical study.
Right.
So you're really looking at what's the observations and what do you see in the distribution, and is it representative of sort of the distribution we're seeing here? That's a good question. No, we haven't done that. That we should do.
Okay.
I just looked at sort of the bounding case of asteroids that we've seen with spacecraft primarily, right? Yeah, so porosity for sure. So like Didymos is a C-type or B-type. Actually, Ryugu might also count as one on that stellar at the end, although Ryugu seems to be maybe closer to the sort of mean sort of range of numbers that we're generating here with the input conditions. I don't know if that's what you were asking, Andy. Any other questions?
Yeah. Could you, maybe I've overlooked it, but could you also, with his calculations, predict the shape of Didymos, which is unconstrained by observations?
You could probably. We haven't looked closely at looking at moons that then stay in stable orbit around the primary, although we could. You know, I just focused on just looking at all the aggregates that we were generating and then looking at that. But clearly, PKD-Grav will allow you to watch all that and the evolution of primaries. I don't remember, maybe Patrick can remind me whether we see a lot of moons sort of hanging around a primary for a long time in these simulations. We do in some instances. Okay, he's shaking his head, yes. So we should definitely look at that. That's a very good question.
I think the moon is also distorted by tidal forces, so it's a bond rotation, so I expect it's not quite the typical most aggregate, the case, the shape you find in most cases. But
I also think that down the line, maybe with Yun, we should think about doing spin-up cases and then looking at what those shapes end up being after reaccumulation, after they've disrupted like she's shown.
Okay. All right.
Any more questions?
All right, then let's thank our speaker once again. Thanks.
Okay, our next speaker is, and the last one I think before lunch, is Ettore Perozzi, who has 3 addresses. The first one being the European Space Agency Space Situational Awareness Near-Earth Observation Coordination Center in Frascati. And I hate acronyms. And the title of the talk is the ESA SSA-NEO System Evolution.
Thank you. Good morning. So what I'm going to talk is about, you see it's the result of a large teamwork, not only from the scientific side, but also from this industrial side. We are the team that is supporting the development of the, what we call the SSA-NEO system. So what we are talking about, this is, let's make a little history. As you know, we in Europe at ESA, things are developed through contracts to the European industrial community and the scientific, supported by the scientific community. So since 2009, we had a sequence of contracts which led to the development of what we call the SSA-NEO system. In the presentation by Detef Koshny, you saw, let's say, the strategic view of ESA with respect to planetary defense. And what we are focusing today is on one part of the system, which is mostly concerned with the NEO software, the software and the data processing functions. You will see that the observing part is nicely handled by a poster by Marco Micheli. So here is what we are going to do, what we should, how to make our system run and how we can improve our functionalities. Essentially, what we make all our data available through our web portal, which is publicly available at the SSA website, NEO website. Just to mention, we have, so you see the menu on the left, we have several functionalities. For example, one which is mostly concerned with this session is what we call the advanced search. We have two data providers. From one side, EARN database maintained at DLR by Gerardan that is providing us the physical characteristic, and then we have the NEODICE site that is giving us the orbital characteristic. We have an advanced search function that makes you peer through our database, mixing up, filtering through both orbital and physical characteristics. This is a unique feature that we would like to further improve, as you will see in later on. This is just to show you how our system has developed over time. These are the names, these acronyms are names of the contracts, but you saw that this always has been steadily increasing in terms of some functionalities. We always try to keep a balance with the NASA side. I mean, we don't want complete redundancy. We want to be complementary to what they are doing, apart from some, of course, basic information, so that you don't have to jump from one side to the other. So here are some of the most recent, in red, the most recent functionalities that we have added to our system. I will show you some of them. For example, we had just developed a nice flyby visualizer. I knew there was a recommended settings, I presume. And let's see if it's working now. Yep. Good. Okay. So as you see, we have a table of flybys, and you can select an object and then have a plot of the flyby, a three-dimensional plot that you can. It's interactive. You can move your point of view. You can change the orientation of and the center of the plot. You can add some additional features, such as the direction of the sun, the axis, and so on. What is, for example, also the boundaries between the various nations. And what is interesting is that we are using then, of course, we have the trajectory. The green line is the line connecting the closest approach point to the Earth. And then you see we have the trajectory of the asteroid, which is the blue one. And then we have the error ellipse. Now, this error ellipse, as you see, is not computed as a Monte Carlo, let's say, simulation with dots, but it's the real ellipse, which is computed through propagating the error matrix, the error ellipse. So this is something which is very useful and that you will see also. Oh, you don't see it. Why you don't see it? Oh, why it's not working? Sorry. I see it on my screen. Okay, don't worry. I will just jump. Sorry. This is funny. How can I do? No. Okay. This is not. This is something tricky because you see the movie is starting, but it's not displayed.
Okay, mysteries of the computer science, but fortunately I had a slide, a backup slide, which was showing you what you missed, which is what is mostly important. You see, okay, this is you can interact, as I was telling you, it's an interactive system. What is interesting is that we have the error ellipse, the whole error ellipse, which has been computed analytically. So as you see, okay, you can move the point of view and everything. We are now upgrading to the more advanced web technology to allow an easier interaction. So we used it, for example, to study the polar encounter of 2016 RB1. And another similar project has been to develop an impact corridor system, and you will see the details in Fabrizio Bernardi's presentation. But as you see, again, we are computing it using advanced algorithms, and you can play with it. You can add the various sigma levels. You can have two altitudes, for example, at 100 kilometers and on the ground. And you can easily plot, for example, what is the effect of adding observation to the width of the impact corridor. And then we are also giving we are now developing ancillary diagrams, additional information. For example, you may ask, what is the behavior of the impact probability over time as the observation progress? And it's not a 3 year, because it depends from the dynamics of the object. It can drop down, but then raise again, as it happened we did this study for the 2017 BL30 object. And then, as I was saying, we are updating our web technology, and we will have soon available, we are reviewing all our orbital visualization tools, including the animations. Then in our site you can download the software that then you can freely use. For example, we have this the synthetic NEO population that has been recently developed by Granvik et al. Under an ESA contract. You can find it there with all the software for using it, a nice interface. And the same, we have a propagator in case you want to do this is not the whole population, it's just a targeted propagator. I mean, you have one object, you want to study that object, you have the package there, you can download it. We have a nice chronology page that is kindly provided by Karel van der Ach, which is regularly updated. And this is something I would like to talk, which is the fact that okay, all these things we are developing it, but we are inside an agency, and we have an industrial team. We have some rules before publishing, making a software available. We have to test it, validate it according to some industrial procedures. Now, it's not that easy because, as you see, we are not satellite operators. The NEO business, NEO hazard monitoring is not an activity which is consolidated, is still in progress. So we had to find a balance between engineering and science in having this system, making this system available. So some of the functionalities that you have seen are still in progress, should be have been developed, but they take some time to make it to the portal and being reliably publicly available. So if you don't find some of them, it's just a problem of being they are just on the way. Now, what we want to do? Well, the phase 3 of SSA, phase 3, Space Situational Awareness, phase 3 will be very rewarding, because we will then do some big steps. We will, of course, continue the web portal evolution and maintenance. I mean, new functionalities will be designed and implemented, but a big step will be the complete NEO-DICE migration. As I told you, we are now just displaying most of the data which are computed by the NEO-DICE, but the whole system is going to be migrated into the NEO Coordination Center. So we will produce our own data. Then another big step will be we have collaboration with the NEOShield-2 EU program to improve our physical properties database and ingesting their results and all the results of their observational campaigns and models. Then we have a general view of as our database increases, we need
more skilled software to handle of this database. So we have a project for data management, and then introduce some education and public outreach functionalities and possibly material on our site. On this, let me finish just mentioning that we have faced this risk communication issue. We had a very nice meeting at Estrin just after the previous Planetary Defense Conference. Here you see Enrica Battifoglio. She's the responsible of a communication Italian press agency, in the typical Italian attitude of saying, hey, what is this impact probability all about? And then we had a very nice asteroid day last year, and we had a very peculiar finding, because we found a very old magazine back in 1966 of an Italian. You see that it was one of the first time that this issue came up on the news. And here you can see that the end of the world is not near, of course, and a new deflection strategy. If you're living close to the Pope, you see, you're pretty sure you will not be hit by a meteorite. And it was very interesting, because inside there was also an interview to an astronomer. It was one of the first time we were not on the moon yet, and it was one of the first time that an astronomer, I think an Australian one, was interviewed. He said, "But we have space missions now. We can deflect an asteroid." But it's peculiar, this magazine, because inside the magazine there was also the first public appearance of Andrea Milani, as a top student, Italian top student in 1966. So that was it. Thank you.
Thank you very much. Do we have any questions for this speaker? Yes, Ed.
Fantastic work. What's your timescale for doing all the migration? What's your timescale for doing the migration and all these upgrades and to the website and new capabilities?
Sorry, when?
What is your timescale for completing all the things that you talked about?
I think in a couple of months we will have the functionalities that I showed you already ready. I mean, like the flyby visualizer, the impact corridor, and all these things. And it will take some months, I think, 2 or 3 months yet. And then for the one in the list at the end of my presentation, I think it will take years. For example, the NEO-DICE migration is a big issue. You have to. It's a big software. But we have this 4-year phase 3 timeline. This is our goal. The big issues there will be over within the 4-year time frame of the SSA phase 3.
Formal declaration. The migration of NEO-DICE must be complete by October 31, 2018. Because on that date I retire. So either NEO-DICE is transferred to ESA or it will close, period.
So now you know. Any other questions? No? Well, I think pretty well exactly on the dot. We'll finish and take lunch. I'd like to thank all our speakers for keeping to their allocated times. You've done very well.
Just one. This is a nice part, because as time went by, we had a scratch map, and every time we got a connection from a foreign country, we were scratching it out. So this is the history of our center. In the end, we had a lot of nice countries connecting.
Okay, I guess we meet again at 1:30 for the continuation of session 3. Thank you. The first talk of the afternoon by Xiaobin Wang from Yunnan observatories, Chinese academy.
And the information about the new observation. Last is the summaries. Photon is Apollo type near-Earth asteroid, and it has a very small values of the perihelions. So it was hitting periodically, and the dust tail and the dust activity were detected around its perihelions. So it is called rock comets or active asteroids. As for the spin parameters and shape, till now, several groups has do the light curve analysis for finding its spin parameters and the shapes. In short, we have the 3 candidate pole solutions. Here we mark the solution 1, 2, 3. These 3 pole solutions has the slight difference, especially in latitude. Based on the earliest spectral data, Lu and Binzer's data, it was tried to explain the spectral variations with the heating effects. They predict a more bluish colors in the north hemispheres than the in south hemispheres. They use the pole solutions of the solution one port to explain the spectral variations. But this is a distribution of the slope of this spectral. There is no stronger relationship like they are predicted. Recently, Kinosto's data show there is spectral variation along the longitude or the rotational phase. So why we do the observation for this asteroid? We want to refine the pole solutions and to understand how the spectral vary over the body of the photoms. We do the photometric observation and the spectroscope observations. One 2.4 telescope at the Lijiang site of the Yunnan observatories was used to do the photometric data and spectroscope data observations. Additional 2 small telescopes. One is at the Lijiang site, and another is at the Ali observatories, was also used to do the photometric observations. The result of that data analysis, the light curve inversions. Besides our new observation data, we collected the existing data. So in all, 16 light curves are involved in our light curve inversions. Our light curve inversions actually contains 2 steps. One is the convex inversions, and the second step is the virtual photometric Monte Carlo simulations. This is we derived the pair of the pole solutions in the convex inversion steps. And this is the shape corresponding to the pair of the solutions. They look a little different. Now, we add our pore solution here, which more close to the solution 1 and 2. There is interesting things happened during our analysis. So this is IMS fitting, IMS of the fitting. Here is this our observation data have a large IMS. So if we back to check the light curves, we found there is a fluxy shift in one night. And we also checked this point, this data. It also have the similar flux shifts. So we don't understand what's the happen. This picture is the result of the second step, that is virtual photometric Monte Carlo simulations. In short, by this step, we can get the joint distribution of the spin parameters. And this first row is for the pole 1, and this is for second poles. Based on these distributions, we can estimate the uncertainties of the spin parameters, which rose mainly by the observation errors. About the spectroscope observations, these tables listed in details information about the observations. Last column is the number of the spectra we derived in that night. For the data reduction, the solar analog stars and the standing flux stars also observed at the same night. This is reflector spectrals on the first night, 5 January 2016. And this is the second night. Actually, in that night, we actually get the eight spectrals. But due to their contaminated by the stellar light, they were not used here. From the spectrals, we can see the shape or the slope are different in the one night. Oh, okay. This is third night. Also, we remove the contaminated spectrals. These figures I want to show the two spectrals obtained at the difference time, but which has a similar sub-Earth locations. They have the similar spectrals. Similar to the Okasoka's ideas, we also calculated the aspect of the sub-Earth, and we also put their data, the red cross, into our data. So the black cross is our data, and all the slope was corrected. The phase render effections. From these figures, there is another data point. According to Augustus predict, the north hemispheres should have the negative slope. So they should have it there, but our observations located here. And we also calculated the longitude of the sub-Earth, of each sub-Earth. And we have the similar triggers as the Kinostos distributions. Summaries. Based on the extending data, because our data is 1 year, more 1 year longer than the previous results. So we gave the new solutions. And the flag shift in one night is need to understand the reasons. Our spectral scopes data contains B type and C type like the slopes. So especially the spectral of the north middle have the large positive slope. This inverse to the predict by Otsuka. Thank you.
Thank you very much. Do we have any questions? Andy. Just a minute. Andy first.
Thank you for your talk. Phaethon is a very interesting object, so it's good that you're looking at it. There have been at least two other low albedo asteroids that also seem to show spectral slope differences as they rotate. Bennu and 1996 FG3. Have you compared Phaethon to those to see if the amount of slope change is similar?
Sorry. Can you repeat?
Sure. You see spectral slope changes on Phaethon as it rotates.
Rotates, yeah.
There are two other asteroids that are B-type or C-type that look like they have slope changes as they rotate. Bennu and 1996 FG3. Have you looked to see if they are similar in how their slopes changed, or if not, you might? Are you considering doing that?
Sorry, I will check back. I don't check you mentioned the asteroid data. I will check back when I'm back. Sorry.
Okay, great. There was Boris, yep.
About the spectrum resolution.
Typical 300.
Okay.
300.
Okay, let's thank our speaker again. And we move on to the next talk.
Is Jesse Dodson. Thank you. And she's talking about near-Earth asteroid characterization for threat assessment. Thank you.
Okay, fantastic. All right, so
I have the privilege of working with a team at NASA Ames on asteroid threat assessment, and I'm going to talk to you about the characterization side of it a little bit. And so I started out as a physicist, so I break everything down to the simplest possible starting point. And you think about what kind of characteristics are you going to need to understand the kind of threat an asteroid might hold. And throughout my whole talk, I'm assuming the asteroid in question is going to hit. That's a given for me. So you want to know, where does it hit? Location, location, location. How much energy is it bringing in? So 1/2 mv squared. And you want to know what it happens as it goes through the atmosphere. To that, you need to know your velocity, your density, some sort of strength parameter to tell you how it's going to break up. And so to start off, let's see, what do we know about those things? Well, we have an orbit from which we can get an impact, location, a velocity, and angle for every asteroid that we know about. Luckily, none of them are likely to hit, but we're going to assume that if one was going to, we would know that information. Diameter, well, we heard about radar earlier, and there's a lot of radar objects, but when you count up the ones that have a very precise diameter, there really aren't that many. So if you want to have a radar measurement with a diameter about 10 plus or minus 10%, you're looking at, a fraction of the known near-Earth asteroids. We do a lot better when we look at the NEOWISE and Spitzer data sets where we use the infrared data and NEADM. You get something just under 10% of the known asteroids. We have a diameter somewhere in the 10 to 35% range accuracy. Density, that one's really scary. We know very little about the density of near-Earth asteroids. We have so-so measurements on a handful of them. And the arrow strength is scarier yet. But we're not daunted. We're physicists. We move on. Oh, let's get a laser pointer here. This is great. And then the other thing, just as a point of caution, is here I've got just the count of I think this was there were 16,210 asteroids in MPC last week when I pulled this up to make this plot. And here you can see the distribution H magnitude for the known asteroids. And here's the one data set for which we have a fraction of the known asteroids where we have information is this blue set. We have diameters from the infrared. And we got a bunch of them, but you can tell they're on the brighter end, so they're larger. But all is not lost because, like I said, we're physicists, so we make inferences. And this is like a whole other talk. And if you want to talk to me about how you make the inferences, I could go on and on for probably 3 times as long as I have, so catch me at a coffee break. But so here, for example, standard thing, you infer your diameter from an albedo and your H measurement. Of course, you don't really know what your albedo is, and so if you want to be careful about it, you get a distribution rather than a specific value. And so here, this line here is the nominal size you would get. It's about 150 meters for a H equal 21.9 magnitude object. I saw Paul somewhere. Thank you, Paul, for giving me an example to work off of. And so you see you get a distribution of diameters, which is certainly not Gaussian, certainly not symmetrical, and a little bit scary. Density isn't a whole lot better. Like I said, we don't know the densities of many asteroids, so the current inferences we're using for densities is we start with the meteorite densities, we apply a porosity model, which is informed by the few asteroids for which we do have measured densities, and we end up with a distribution of densities, which, if anything, is less Gaussian than our distribution of diameters. And here for reference is a kind of the mean for this distribution is here about 2.1 grams per centimeter cubed. So how do you turn messy distributions like this into anything to assess your threat? Well, at Ames, we've developed a probabilistic asteroid impact risk model. This is largely Donovan and Lorian's child with lots of inputs from the rest of the team. And so up here, we start with the asteroid characterization, and I kind of gave you some hints about how we then infer a distribution of input parameters. using that distribution of input parameters, we Monte Carlo sample across all those distributions. I just gave you a few of them, but we can Monte Carlo sample across many, many distributions. We can run millions of cases. We actually run them through the atmosphere using the meteor equations. We've got a fragment cloud model, which gives us a model of how the object breaks up. It bursts at a certain altitude, and then we propagate the radiation down. And before you ask me too many questions about the details for anything below this line, let me give some shout outs to how you can learn more about this later this week. Lorian is giving a talk Thursday morning where she's going to describe the fragment cloud model that was used in this work. Michael Aftemus has a poster this afternoon where he talks about how we turn airburst altitude into blast and radiation damage. Thursday morning, Donovan is giving a talk where he applies this entire model to the problem of the total ensemble risk. And if you want to get some previews about where this model might be going in the future, Thursday morning, Eric Stern is giving a talk about some advances we're doing to learn more about ablation. And Daryl Robinson does hydrocode models that we use to kind of benchmark the engineering models that we can run millions of times. Daryl can't run his model millions of times, so we just compare occasionally. But so what can this model tell us about what we want to know about asteroid characteristics? And so let me walk you through this particular plot, and just in case I run a slip, I call this a lornado. It's our nickname for it because it looks like a tornado and it's made by Lorian. So if I say a lornado, you know what I mean. And so what this is showing here is on this top bar, we're varying all the parameters. We're sampling all the Monte Carlos. And you can see that the affected population, okay, I did the nasty thing. I took 0 off the plot just to make it more readable. These bars do go all the way to 0 because we have some places where there's no people. So what this bar is showing me up top is if I vary everything, my maximum affected population for this H equal 21.9 object is just below 10 to the 8 people. This dot here is the mean. This is kind of your key if you forget what I said. That's the mean number of affected people. That's your 95th percentile. And this line in the middle is what we call the baseline. And the reason that's important is you go to the next bar, I hold all the other parameters at the baseline and just vary the location. Similarly, size, I hold the location, the velocity, the density, the angle, the strength constant, and just vary the size. And so you order these by how big of a difference as you sample over that distribution that parameter can make in the final outcome. And it kind of starts to help you inform your intuition. Well, it's not surprising that location is really important. We know location, location, location. Size, not surprising that it's pretty important as well. Velocity, density, angle. You know, this makes a physicist's heart happy, right? This is kind of what you would expect. But, you know, we don't stop here because we're physicists. And so let's add some more information. Let's say we can go to the telescope and get some more information about the object we're interested in. I'm not sure yet if Paul's going to let us know more about PDC 2017, but let's pretend he did. So let's say we went out and said, okay, let's have a taxonomic class for this object. From that, once I know the taxonomic class, I can infer different distributions for the densities and for the diameter. And so here again is the nominal diameter as the line. The green shows the distribution of diameters I would get if it's an S class. And so you can see it actually gets smaller on average. That's kind of happy. If it's a C, it actually kind of gets bigger on average and kind of keeps going and going and going. And your M classes are kind of right there in the middle. I can do the same thing for the densities. And again, I've included the nominal density from the entire population case as a line. And you can see the C's are less dense, the S's are about the same, the M's are more dense. And so now I go to a set of Lornados where I've divided them by class. And again, it's the same thing where the location, I'm holding everything else at its baseline and only varying the location. And I don't expect you to remember the order of the characteristics from the first slide. So here I've given you little arrows as memory aids. So here, for a C class, the velocity actually becomes more important than it was for the general population, which is somewhat unexpected. And the size actually becomes less important. The S's, it all stays about the same. And the M's, the angle that it comes in, the entry angle, becomes more important, and the density becomes less important. And you'd think, well, why can the density become less important? It's a dense object. Well, to some extent, the fact that the density is high and is a fairly narrow distribution tells us that going out and learning more about the density of an M-type object isn't going to give us a whole lot of new information about the threat. But knowing its size would give us a lot of new information. And you can keep going down this rabbit hole quite a ways. And so in this case, what we've done is we actually took, rather than just a whole bunch of random locations and all the entry angles and velocities that are possible, we just looked at what was on day one for the PDC approach. And again, it's location, size, but your velocity is no longer of a huge amount of interest. It's fairly, actually, this particular scenario, the range of velocities is pretty narrow. And so we know what we need to know about that one. And you can play the same game with your classes, but I see the red light flashing at me. So I'm going to go just one more and just give a shout out. So as we go through and put together data so that we can generate these distributions and start to make these inferences, we're actually putting as much of this information as we can up on the web for people to get access to. And so we have both asteroid contents, taxonomic classes, diameters, and albedos. We also have a meteorite side because we're a big believer that they're samples of these objects we're studying. You can only learn so much from them, but still, they are samples. And so we've also got tables of densities, porosities, compressive tensile strengths, elastic and shear moduli, and heat capacities and thermal conductivities there for the taking. All right, thank you very much.
Great work. Have we questions? Yeah? Yeah.
So I have lots of questions, but I'll confine myself to one. One of the things we keep discussing at these PDCs are things like scout missions and such as that. It would be interesting to take what you're doing and go beyond this to the mitigation step. What is the probability of success or failure for various mitigation options? And then given additional information for designing that mitigation option, what is now, how does that change your probability of success? Time-based, how much time do you have to develop the system, all those sorts of things. But I think we could find the right set of physicists to come up with some distributions for you to include if you're not already doing that on extending it all the way through.
That would be really fascinating. That's, a side of modeling we haven't even touched yet, but this approach could absolutely apply to that.
Yeah, I think we should look into doing that. That'd be fun.
Cool.
All right, then we have President Chapman on here. Yeah, I think I'm closer.
Yeah, I'd like to just talk about one example that you highlighted, actually, M-types. Mm-hmm. I'm inferring that you are assuming that they're metallic.
Yeah, I am.
And first, I mean, M is defined in terms of albedo and spectrum. So determining that it's metallic is a good guess in general, but there's a lot, there's people, Andy Rifkin and others here can tell you a whole lot about uncertainties about what M's are really composed of. And so there are uncertainties you're not taking into account here.
Well, I kind of, you're right, but not entirely, because I kind of glossed over exactly how I determined it was an M-type. But in a real problem, you're absolutely right, and that gets into the other half-hour talk that I'm not giving, that I'm not done with. I'm not done with that work yet. Don't get me wrong. I'd love to talk to you and Andy about that more.
All right. I think time is up. Yeah.
Right, let's thank our speaker again. And now for the final talk of this session, we have Shinsuke Abe of Nihon University in Funabashi. And he will talk about size and orbital distribution of interplanetary dusts associated with near-Earth asteroids by Mu radar meteor head echo observations.
Okay, thank you, Chairman. So this is the last talk before the afternoon coffee, so please wake up. So today, probably my talk is the smallest Earth impactor during this conference. So I'm talking about several tens microns in diameter by radar observation. So this is a brief summary of the Earth's influx as a function of size or mass. So today's topic is this size, several tens of micron to millimeter size. On the other, there is another opportunity to observe the centimeter size to meter size by the lunar impact flash. So before my talk, I would like to introduce our another mission going to the Earth-Moon Lagrangian 2 point by the small CubeSat, which will be launched by NASA SLS in 2019. So we are developing onboard small cameras to detect the lunar impact flash just behind the moon. So because we can observe about 100 times much larger area compared with the single camera on the ground base. That's why the opportunity to observe the larger impactors can be revealed by our mission. So detail will be shown by the poster by my student, Mr. Fse. So this is our, so actually this week, the thermal vacuum test is ongoing. Okay, so radar. So this is our radar operated by Kyoto University, which is located at the Shigaraki Prefecture. So the diameter, effective diameter is 103 meters with the 475 cross-ear antennas with the maximum power is 1 megawatt. So it's very, very strong power, and we generate the very concentrated beam to the zenith. So the effective field of view is about 5.5 degrees. It's very, very narrow beam, but very powerful to detect the very faint meteors. So we have 25 channels in these regions, and the pulse radar is generated about at 332 times per second. And each, we have interferometer in these regions. We can detect not only the relative velocity, but also the trajectory for every single particles. So far we have more than 18,000 orbits in hand since 2009 observation. This is just summary of our detected the radiant point on the sky. So be careful because our observation is biased by the Earth's rotation around the sun. So the apex region has a much higher velocity because it's Earth's velocity is added. And so anyway, every single particle has their orbital elements. For example, we have more than 1,000 Gemini's orbital elements, and for example, another quadrant is meteors. So compare with the near-Earth object population. So this is just an example, perihelion distance and the fraction of near-Earth object. And after debiased here. So this is the current situation of near-Earth object. So compare with our radar result, we have advantages to observe the small perihelion distance particles because we can observe near the sun. So this is another plot to show the orbital elements by same major axis and eccentricity, and the colored show the Tisserand parameter regarding with the Jupiter. So of course, our observation is biased. We can just observe at a single point from the Earth. But from this plot, I can say that more than 50% are asteroidal origin. Okay, so for example, this concentration is caused by the Geminis here. And we also have the advantage to observe daytime meteor showers. For example, we are now interested in the asteroid Icarus. So Icarus also has some fragmented bodies we detected by the radar. So we are still continuing this observation. So my students had several presentations related with meteor showers and asteroidal physical observation by spectrographs and so on. So please visit these posters. So because Earth impactor has the bias by atmospheric density and velocity and entry velocity and entry angle, we can remove these biases to compare with each particle's strengness. So here I use the separator parameter. So after this bias, we can compare the strengness of the meteoroids in this plot. So x-axis shows the initial velocity, it's entry velocity of each particle, and the y-axis shows the beginning height. So simply understanding, so if the particle with the higher velocity start its aberration at the higher altitude. So, however, you can, as you see, for example, there are very strong particles or refractory or dense particles here, which can show by larger KB parameter. Even within the same meteor showers, for example, Geminis or Perseids shows a variety of strengness in their dust trails. So for example, Geminis has very strong particles. It's actually these particles is not such big as we expected. So because our radar is the most powerful method in the world, we detected a very high altitude particles. So for example, these particles is so-called fragile dust ball I named. So these particles are very interested because they start their operation at very high altitude with very low velocity. So of course we have the orbital elements of these particles. In this plot, these fragile dust balls, most of them are coming from the asteroidal origin, as you see, these green dot and blue dots here. So because radar observation is biased by the entry velocity, we can now observe such very slow entry object. And we have another problem for radar, so-called radar cross-section problem. So we want to know the size distribution of these particles. However, the radar cross-section is not the only the function of size, but the function of combination of chemical compositions and entry speed, atmospheric density, and also radar directivity. So we have to know this relationship. So in order to investigate radar cross-section to know real size of meteoroids, we made some simultaneous observation with optical cameras. So we did some campaign to observe the same sporadic meteors using very high sensitive cameras up down to maybe 9th magnitude. So this is the first result, the comparison between radar cross-section and the visual magnitude of very faint meteors. As I told you, the radar cross-section is also affected by the entry velocity. So I just divided into two types, the slow Earth impactor and the fast Earth impactor. So anyway, so this plot is not perfect. We plan to make a simultaneous observation with Schmidt telescope observation. So this presentation was done by Dr. Osawa yesterday. So I will skip in detail. But anyway, so now we can convert it from radar cross section to the magnitude. So this is the magnitude distribution for more than 15,000 particles. So for higher speed particles and it's lower speed particles. And also we have the Gemini's information. So this is a power law slope of each particles, and interestingly, Gemini's is truncated for the faint or smaller particles, probably due to the old dust trail. Those smaller particles are already blown away. So we plan to do the simultaneous observation between radar and Schmidt telescope in this winter, because the distance between two stations are very moderate to make a triangulation observation. So last year, Dr. Osa's group did the test using their camera. So there is a meteor here, very faint meteor. Can you identify by your eye? The answer is here. So there is a meteor. So to make sure, this is a plot. So using the half transform algorithm, we can detect such faint meteors, and we made some the photometry of these meteors. And to review, the limiting magnitude is almost 13th magnitude. So last year we did, Dr. Osawa did the test observation. So within 5 hours, they detected more than 15,000 events, and the detecting rate is 15 meters per 3 minutes. So interestingly, we also can detect these very low resolution spectroscopy for faint meteors down to 9th magnitudes. So at least we can say the rough abundances like magnesium, sodium, and oxygen. So this is a very tentative result of radar size distribution and Schmidt telescope. So as I can say that both are limiting magnitudes almost identical, about 13th magnitudes. So using these two facilities, we can review not only the size distribution, but also their compositions and origin of these small particles. Another interesting topic from our radar is we detected asymmetry of pre-perihelion and post-perihelion meteoroids. So we are not sure. So we examined these data carefully, and probably this is the real asymmetry. We are not sure this is caused by fragmentation or not. So last year, Dr. Granvik suggested that every NEOs can be super catastrophic breakup when these particles approach to the sun, typically less than 0.2 perihelion distance. I'm not sure, but the same things happen to the smaller size. Okay, so we plan to make some artificial meteor test in order to get the radar cross-section using the already known parameters, artificial meteors. I'm one of the development team of this project. So we have now the company in Tokyo, so-called AIR. So we are planning to launch this small satellite next year. So first demonstrate will be done in early 2019. So we will release the small particle to within probably 40 minutes. These particles can enter the atmosphere to generate the artificial meteors. So my laboratory is now developing the special material to enhance the light of these artificial meteors. And probably during the 2020 Olympic, we can enjoy these artificial meteors. And this is the Earth Impactor Conference. So our artificial meteor is not the space debris, but controlling vacuum cleaner. Thank you very much.
I think that's a great talk to end this session with. We just have time for 1 or 2 questions. Everybody's very eager to get the coffee. Nobody at all?
What is the size of your artificial meteoroid?
It's about 1 centimeter. It's very small. So that's why the entry velocity is too low to enhance the light. So we need some artificial, company secret. Pardon? Material. Yeah, it's company secret. Sorry.
Do we really understand what is causing Phaeton, an asteroid, to lose dust like this? I mean, it's very robust little bits of gritty dust, isn't it, that penetrate deep into the atmosphere. Is it to do with the perihelion passage and the sort of thermal fragmenting the surface or something?
Yes, if this hypothesis is adapted to such small size, probably also the small particle can be break up when the particle approaches to the sun.
Okay, that's it then for session 3. Thank you for being so attentive. I thank our speakers for their wonderful talks and keeping to the time limit. There's now a coffee break for 30 minutes, so we come back here at about 2:45.